Hello students, my name is Akash Gupta and I welcome you all on Physics Wallah. So in this course, I'll be teaching you all 12 topics starting from complete electrodynamics, then ray optics, wave optics, then modern physics, and in the last we will discuss few topics like semiconductors, electromagnetic wave, etc. Okay. So we will begin this session with first topic, electrostatics. Let me tell you how we will proceed in the course. In every chapter, I will tell you complete theory in short, and then we will discuss important questions and mainly PYQs of NEET and JEE mains. Okay, so this course is going to be very beneficial for you, and I'm sure if you see these lectures properly, if you follow these lectures properly and solve the questions, it will be very beneficial for you, right? And you will have a good understanding of topics after looking at the lectures. Okay, so topics to be covered in this lecture today are: we will study electric charges and Coulomb's law, electric field, potential and energy, electric dipole, electric field and potential due to different charge configurations, dipoles electric field, dipoles potential and dipoles behavior in external electric field, okay, Gauss's law, and finally the behavior of conductors in electrostatic equilibrium. So let's begin. The whole story starts with electric charge. So let us first learn what is electric charge. It is a fundamental property of matter. It is a fundamental property of matter particles, okay, and it is responsible for all electromagnetic phenomena. What are electromagnetic phenomena? Actually, every phenomenon that we can observe in daily life, except gravity, every phenomenon is electromagnetic. All chemical reactions that you study in chemistry are electromagnetic in nature. Every reaction that happens at atomic level or molecular level is electromagnetic in nature, right? The forces that you experience except gravity, I said except gravity, the tension force is electromagnetic in nature. The normal force acting on us is electromagnetic in nature. The spring force, the friction force is electromagnetic in nature. So obviously the study of electromagnetism becomes very important. The light is electromagnetic in nature. So let us first learn what are the properties of charge. The charges are of two types, positive and negative. You all know that. Charge is scalar, charge is additive. Additive means if you have a charge Q1, you add a charge Q2, the total charge becomes Q1 plus Q2. Or if you add Q1 and minus Q2, the charge becomes Q1 minus Q2. The charge is conserved, charge cannot be created, charge cannot be destroyed. Charge is quantized. Quantized means actually the freely available charge, the minimum freely available charge in the nature is charge of 1 electron. So you cannot have charge of 1.5 electron. You cannot have charge like root 3 electron. You can have charge which are integral multiple of 1 electron's charge. So you can have charge of 100 electron, you can have charge of million electron, you can have charge of 2 electron. So any charge on any body on earth will be equal to Q equals to integral multiple of electron's charge. It may be positive or negative, but non-integral multiple of electrons charge is not possible. Suppose you have 3.5 electrons charge, 3 electron is possible, but from where you will get 0.5 electron charge? That is impossible in nature. And the last property is the charge is not dependent upon frame of reference. You observe charge from any frame of reference, it will be same. Okay, so charge is independent of frame of reference. So let's start Coulomb's law. You all know if you have two like charges plus and plus, they repel each other, and if you have positive and negative unlike charges, they attract each other. This force acts along the line joining them. Okay, and the magnitude of force is given by Q1 Q2 upon 4 pi epsilon naught r square. This 1 upon 4 pi epsilon naught r square, this 1 upon 4 pi epsilon naught is also called K, and the value for K is 9 into 10 to the power 9 in SI units. Okay, SI units. So if you are dealing charge in Coulomb, force in Newton, R in meters, so you have to put K as 9 into 10 to the power 9, right? There's one important fact about this, I think you must know. Suppose someone fills this entire space between two charges with some homogeneous medium. If this space is filled by a homogeneous medium, will the charge Q1 will apply some different force on Q2? Will the force between the two charges change? Just think of it. And answer is no. The charge Q1 applies same force, this force on Q2, and Q2 applies this force on Q1. There is no change between the force between charges. There is no change in force between the charges. But what happens? What happens if we fill a medium? So if we fill a medium, the medium gets some electrical polarization, some electrical effects, and medium also starts applying force on the two charges. And because of medium's force, the net force on any one charge is changed. And if medium is homogeneous and very large in size, the net new force, the net electrical force on any charge now becomes Q1 Q2 divided by 4 pi epsilon naught epsilon r square. A new term appears, epsilon r. It is actually the relative permittivity of the medium that is filled between the charges, in the space between the charges. So remember, the force between charges does not change. Charge is still apply the same force on each other. It is the force of medium. Because of that, the net force changes its value, right? Okay. To begin questions, let us first discuss the Coulomb's law in vector form. So suppose in some question you want to find force on Q2 only. Suppose you want to find force on Q2 only. The force is acting on Q2, but it is being applied by Q1. What do you have to do? Just draw a vector from Q1 to Q2. Remember, this is a position vector and the head will be towards the charge on which force is being applied. And the tail will be on the charge who is applying the force. So if you want to find charge or force on Q2, head should be towards Q2. If Q1 is applying the force, tail should be on Q1. And then the force on 2 because of 1, force on 2 because of 1 is given by K Q1 Q2 divided by R cube multiplied by R vector. Surprisingly, this force is in the direction of R vector. This force is in the direction of R vector. So this formula works well. You can see, according to the equation, the force is in the direction of R vector, and by observation also we can see the force is in the direction of R vector. So everything is good. Some of you may say, okay, in the force we had seen only R square in the denominator. They are seeing R cube in the denominator. Why? We have R cube in the denominator because we have one magnitude of R in the numerator also. Still the force is dependent upon 1 upon R square only, okay. And one more thing, suppose one of these charges is positive and one of these charges is negative. What will happen then? The force will be acting in the opposite direction of R. The force should be acting in the opposite direction of R, and that you can get if you put sign of charges. See, if one is positive and other is negative, just put Q1, Q2 sign in this equation. If you put sign in this equation, we have an extra minus sign here, and that minus sign will say the force is in the opposite direction of R vector. So this formula works in every situation. Just what you have to do, you have to put sign. You have to use sign of Q1, Q2 in this So always remember, whenever you use formula for force in vector form, always use sign of charges. Sign of charges. Okay. So let's begin few questions. The first question is very important, and surprisingly NEET asked very good question on electrostatics. So I'll recommend you pause the video, study the question well, try to answer it, okay, and match the answer, and I'm switching to solution directly, right? So here we have two charges. Let's say the charges are Q and Q, identical charges, and as the charges are identical, they will repel each other with some force, say F. This is electrical force between them, F. The force of gravity is also acting on the charges, and the force of tension in the strings, let's say that is T. Since there is symmetry on the left charge and the right charge, the symmetry of forces says if you observe any one of them, that will be sufficient. Okay, so I'm observing only one charge. If I take this angle as theta, this angle is theta, and break T into two components, I'll have vertical component as T cos theta and horizontal component as T sin theta. Obviously, horizontal component will balance each other. T sin theta equals to F. F will be K. K is 1 upon 4 pi epsilon naught. Q1, Q2 is Q square because the two charges are same, divided by X square. X is the distance between charges. It is given in the problem. And T cos theta is equal to mg. Just divide these two equations, you will have tan theta equals to K Q square divided by mg X square. There is one more thing the question have said. They are saying the length x, the gap between the charges, is very less as compared to length of the string. So if this gap is very less, this triangle is going to be very thin, this triangle is going to be very narrow, and the angle theta is obviously very small. So let me tell you, if this is theta, this is also theta. And if this is theta, this length is x by 2. This is x by 2 because this is x by 2. And since theta is small, you can write tan theta very close to as sin theta, which will be perpendicular, that is x by 2, divided by hypotenuse, which is L, C. And you can replace x by 2L in the place of tan theta. So if I replace tan theta by x by 2L, let's replace here tan theta equals to x divided by 2L, and bring this x square on the left and rest everything on the right, you will have x cube. See carefully, k is a constant, mg is a constant, 2L is a constant, all these are constant. Let's club them into a one constant c, and you have q is square. Okay, now what we can do, we can say x to the power 3 by 2 equals to root c q, and they have said because of some mechanism the charge on the two particles is leaking. The charge on the two particles is reducing at a constant rate. The constant rate means q is not constant, q is changing, q is decreasing, but its rate of change is constant. So to use this fact, to make use of this fact, I will differentiate this equation with respect to time. And if you do that, you will have 3 by 2 in the front, x to the power 1 by 2, and dx by dt using chain rule of differentiation. On the right, you will have root C and dq by dt. And what they have said the dq by dt is a constant. So you see, root C is a constant, dq by dt is a constant, 3 by 2 is a constant. Okay, so club them again together, and you have dx by dt. Dx by dt means the rate of change of this x. The rate of change of this x is actually the approach velocity of two charges, because the charges will approach with a velocity at which the distance between them will change. Okay, so this dx by dt is actually the approach velocity, and you have x to the power 1 by 2. You bring this x to the power 1 by 2 on the right hand side, so you have dx by dt as approach velocity. Club every constant and you have a new constant c dash, and x to the power 1 by 2 in the right will go x to the power minus 1 by 2, and you see velocity is proportional to x to the power minus 1 by 2. Can you see that? So the correct answer here is A, where velocity is proportional to x to the power minus 1 by 2. I hope you understand this question. If you are a good student, curious student, I must tell you something. There is something wrong with this question. This is a question in a very famous book of physics. I'll not say the name, but it is a very famous question of a very famous book in physics. And the problem is this: you get this result when you consider equilibrium of particles. When you consider equilibrium of particles, see, I have balanced the forces. I have balanced vertical forces here, I have balanced horizontal forces here. And obviously equilibrium is not here because the particles are approaching each other, and that too with not constant velocity. So obviously the equilibrium conditions are untrue. They are not true for this question. So it is actually a wrong question that NEET asked in 2016. So you must notice the fact and nothing can be done about this. Okay, so we'll move further to next question. So now we have a simple question, 2017. Suppose the charge of proton and electron, you know the charge of proton and electron are of same magnitude. If you check this at the 17th, at the 20th place of decimal, the numbers are exactly same. But they are taking a hypothetical situation where charge of electron and proton are different. Charge on electron is say minus E and charge on proton is E plus delta E. Means the proton has slightly bigger magnitude of charge. So again pause the video, try it yourself, and I'm switching to solution. Okay. So if hydrogen molecule has one electron and one proton, the charge of electron and proton because of additive nature cancels out. We have this atom with a charge of electron, delta E. We have charge of delta E on this atom, and on other atom also we have charge of delta E, because other hydrogen atom also has one electron, one proton. Minus E plus E cancels. We have these two extra charges. Okay. Now they say if electrical forces and gravitational forces balance each other. So obviously if electrical forces and gravitational forces balance each other, electrical forces will be of repulsion, and if the mass is m, obviously the gravitational force will be of attraction, and they are balancing each other. If they are balancing each other, what you will do? You will say, okay, gravitational force is equal to electrostatic force. What is the gravitational force? Gravitational force is gravitational constant G. Mass m1, m2, that is m square, because both have same mass, both are identical particles, divided by r square, equals to Fe is k delta E square divided by r square. the distance on the two sides cancels out, and from here you know the value of delta E. So delta E here will be equal to, taking the square root, you will have root G divided by K, root G divided by K m square. You don't have to do exact calculations because they are asking only order, and order 2 is very far from each other. You have minus 23, minus 37, minus 47, minus 20. So since the answers are very far from each other, if you do approximate calculations also, it will work. So I think you remember, sorry, this square is not here, okay. If you remember, the G has 10 to the power minus 11 in it, and K has 10 to the power 9, K 10 to the power minus 9, 10 to the power plus 9. If it goes up, it has 10 to the power minus 20, and 10 to the power minus 20 square root is nearly 10 to the power minus 10. And in mass, we have 10 to the power minus 27. So add it, you have 10 to the power minus 37 as an answer. So correct answer is B. Next question. Here we have 2 point charges A and B having charges Q each, okay, plus Q and minus Q each. And what they have done, they have transferred 25% of charge of A on B. And they are asking what is the new force in terms of the old force. So if initially you have two charges Q and minus Q, right, placed at some distance R, the force is actually, the initial force is actually K, Q square divided by R square. But what you have done now, finally, you have taken 25%, means Q by 4 amount of charge from this charge. So it becomes only 75%, that is 3 by 4 times of Q. This remains on the first charge. And if you put that Q by 4 on this minus Q, this minus Q and plus Q by 4 becomes minus 3 by 4Q, as charge is additive in nature. This is the property of, fundamental property of charge, and distance is R square. So now you can see the new force F dash equals K 3 by 4Q, 3 by 4Q divided by R square. And if you take 2 3 by 4 in the front, you have 9 by 16 KQ square by R square. It is the old force F. So the correct answer is 9 by 16. Okay, that was a very simple question. Let's move on. We have another question. That's of here NEET is not written. This means this is a JEE mains question. Okay. We have three charges plus Q, Q and plus Q are placed respectively at distances 0, d by 2 and d from the origin. So suppose we have this as x-axis, this is origin, and on origin we have plus Q. On d by 2, means this is d by 2, we have the small q, and on d means another distance d by 2, we have plus q again. And they are saying the net force experienced by plus q placed at origin is 0. So force on this charge is 0. Okay. See, as this is plus q and this is plus q, this plus q is definitely going to repel this plus q towards left, right? And if this is going to repel this towards left, this q must attract this plus q, so that the net force on this plus q can become 0. So force by this q on it must be attractive. So this is F1 and this must be F2. F1 is the force between plus q and plus q. F2 is the force between plus q and small q. And because of this attraction, this q should be of negative nature. The small q should be of negative nature. So obviously the two choices cancel each other. It cannot be positive. And if we balance the forces, you know the F1's magnitude is K capital Q, capital Q, capital Q is square divided by distance between them is d square, right? And the magnitude of F2 is K, capital Q, other charge is small q, divided by distance between them is d by 2. So d is square by 4. 4 comes in the numerator we have here. D square got cancelled, 1 q got cancelled, k got cancelled, and we have magnitude of charge q as q by 4. You can see that. But by nature we know the q should be negative, otherwise both will repel plus q at origin, and how can this balance is possible? So the q should be negative. So the correct answer is B. Okay, so that was a very simple question. I think you understand the solution. Let's move further. So after Coulomb's law, we will study what is electric field. Electric fields in this chapter are of two types. One is a vector electric field called electric field intensity, or symbolizes as E vector, and one is a scalar electric field or called electric potential popularly, and the symbol for electric potential is V, remember. So let us understand the definition. If you put a test charge at point P, the force experienced by this test charge per unit test charge is the electric field at that point P, right? The test charge is taken to be positive, so the direction of electric field at the place of positive test charge is in the direction of force. Or if you know the electric field already, if you multiply the electric field with the charge, you get force on that particle. Always remember, if the charge is positive, the force is in the direction of field. If the charge is negative, just use the sign of charge. You will see a minus sign here, and the minus sign will say force is in opposite direction of field. The meaning is, if at some point the electric field is in this direction and you put a charge here, if it is a plus q charge, the force is in the direction of field and given by q times E. Given by q times E. And if the charge is negative, minus q is there. Yes, if the charge is minus q like this, the force is in opposite direction of electric field, but the value is q times E. Okay, so this is electric field, vector electric field, right? The scalar electric field or electric potential is defined by work. So if you want to find potential at some point P, what we will have to do, we will have to bring a test charge, a positive test charge from infinity to this point P. And that work divided by charge Q naught or the test charge Q naught is called potential at this point P, right? Potential at this point P. And because of the work done by external forces, by external mechanism, there is some change in potential energy of the system, and what we say that delta V means the change in potential difference is equal to change in potential energy divided by charge, test charge, or you can say the traveling charge. Okay, so always remember the change in potential difference is equal to change in potential energy caused by this work divided by Q naught. Usually we assume if charges are at infinite separation, we assume its potential energy to be 0. So if charges are at infinite separation, we assume potential energy to be 0. So at certain point P, if you want to find potential difference, Vp minus V infinity, it will be potential energy at P minus potential energy at infinity divided by Q naught, and since potential energy at infinite separation is assumed to be 0, potential 2 at infinite separation is assumed to be 0, these two are 0, you can say potential energy of a particle at P is going to be the charge multiplied by potential at that point P. So this is a very important equation, and this energy is called interaction energy of this charge with the rest of the configuration. Remember, this energy is called interaction energy of this charge with rest of the configuration. Okay, so let's proceed further. What is electric field and potential produced by a point charge? So if we have a point charge means a very tiny, a very small sized charge Q here. If we have a very tiny, very small sized Q charge here, and we wish to find potential and electric field at point P at a distance, at a position vector r from it, the electric field is given by kq divided by r cube r vector, and potential is given by kq by r. You should remember this. If you use this formula in vector form, remember, put sign of charge. And this is a scalar. If this is a scalar, always use q with sign. You have to ignore sign only in one case. You have to ignore sign only in one case. When you want to find magnitude of field. If you are wishing to find magnitude of field, you are interested only in magnitude, you can ignore sign of charge. But if you are using force or electric field formula in vector form, use sign. If you are using energy or potential formula in scalar form, use sign. Okay, so you have to always use sign. If you put q as minus q, the potential will be negative. So always remember, potential can be positive, it can be negative, it can be zero. Okay. In this problem, they have 2 point charges Q1 and Q2. Q1 is of root 10 microcoulomb and Q2 is minus 25 microcoulomb. They are placed at specific positions, and we are asked to find electric field on y-axis at y equals to 3. Okay. So I'll suggest you pause the video, attempt it yourself, and then look at the solution. I'm directly switching to solution. So the charges are placed at x equals to 1 and x equals to 4, and electric field we have to find at y equals to 3. So let's draw. Y axis, x axis. The Q1 is placed at x equals to 1, so it is Q1 root 10 microcoulomb, Q2 minus 25 microcoulomb. This distance is 1 and origin to Q2 distance is 4, and we have to find, this is 1 and this is 4, and we have to find electric field at y equals to 3 at this point, right? Let's begin. Actually, the Q1 is positive and field of positive charge is away from it. So the field of Q1 would be away from it like this. Let's suppose this is E1, okay, and Q2 is negative. Since Q2 is negative and negative charge's field is towards itself, that is why the field of Q2 will be towards Q2 like this, and let's call this as E2. Okay, I'll consider this angle as theta, and if it is theta, this will be also theta. So let's find E1 and E2 first. E1 will be K Q1 divided by the square of this distance, and since this is 1 and this is 3, this distance by Pythagoras, it will be root 10. It will be root 10 square. So let's calculate. K is 9 times 10 to the power 9 multiplied by Q1 is root 10 multiplied by 10 to the power minus 6 because it is in microcoulombs, and divided by root 10 square, that is 10. So E1 is 9 times 10 to the power 9, 10 to the power minus 6 is 9 root 10 and 10 to the power 2 volt per meter, right? This is E1. Similarly, if you calculate E2, E2 will be K, that is 9 times 10 to the power 9, Q2, we are calculating only magnitude, so I am not putting sign of Q2, so 25 times 10 to the power minus 6 divided by R square. And see, the distance of point, let's say P from Q2 is 3 and 4. If you add them Pythagoreally, it will be 5. So this distance is 5 because square root of 3 square plus 4 square is 5. So we have 5 square, and 5 square and 25 got cancelled. So the field E2 is actually 90 times 10 to the power 2 volt per meter. Okay. Since if you look at the options, we have to calculate electric fields X and Y components. We have to calculate electric fields X and Y components. So we will break them into components, and if you break them into components, we have one component of E1 as E1 sin theta and this component as E1 cos theta. And see, if this length is 3, this length is 4, this angle is going to be 53, okay? Or you can say this angle is going to be 37, right? And we have E2, so E2's horizontal component is going to be E2 cos 37 degrees and vertical component will be E2 sin 37 degrees. So now looking at all components, we can calculate electric fields X and Y components. And see, electric fields, net electric fields X component would be, can you see, E2 cos 37 minus E1 sin theta. E2 cos 37 degrees minus E1 sin theta. Okay, let's calculate. I think you all can calculate E2. The value of E2 is 9 root 10 into 10 to the power 2 and cos 37. Sorry, it is not E2. E2 is 90 times 10 to the power 2 and cos 37. What is the value of cos 37? It is simply 4 by 5 if you remember. Cos 37 is 4 by 5 minus E1. So E1 is 9 root 10 multiplied by 10 to the power 2. And what is sin theta? So look at this triangle, sin theta is going to be perpendicular, which is 1, and divided by hypotenuse, which is root 10. So it is 1 divided by root 10. So what we have as an answer, we have, I think, 63 times 10 to the power 2. You can check this calculations, volt per meter. Similarly, you can calculate EY, and suppose we calculate EY, it will be E1 cos theta minus E2 sin 37. E1 cos theta minus E2 sin 37. Similarly, if you put all the values, you will have minus 27 times 10 to the power 2 volt per meter. So we have X component as 6300 and Y component has minus 2700. So if you check the answers, so we have answer as A because it matches with our calculations. So let's proceed further. Next question. This is a simple question, but still I say you pause the video and solve it yourself. Okay. In this question, they are saying they have 27 drops of same size, and these 27 drops all identical. You can consider their radius as R, and since they are charged, you can consider their charges there as Q. and they are charged at 220 volt each. Every drop is charged to 220 volt each. Now what they are doing? They are combining all these 27 drops to form a bigger drop, and we have to find the potential of this bigger drop. See, if we write few equations here, the potential of first drop, or potential of a smaller drop, is 220, and this should be, according to formula for potential, is K times Q by R, where Q is the charge on the drop and R is its radius. Now, if all drops are combined, we will have a bigger drop, and the bigger drop will have 27 Q charge, and let's say radius of the bigger drop is capital R. So the potential of bigger drop is, let's say, V dash. We can write V dash as K times 27Q and divided by the radius capital R. But can we find this radius capital R? Obviously we can, because the volume of 27 drops will be equal to volume of this single drop, because it is the combination of all those 27 drops. So by volume conservation, we can write volume of bigger drop as 4 by 3 pi R cube equals to volume of 27 smaller drops, that is 27 4 by 3 pi small r cube. And if you solve it, you will have capital R as 3 times small r. So in the place of capital R, I can write 3 small r. And now if we divide these two, okay, if we divide these two, we will have V dash divided by 220 equals to 27 divided by 3, that is 9. So V dash will come out to be 9 times 220, and 9 times 220 is 1980 volt. So the correct answer is D. Okay. In this problem asked in NEET 18, they say an electron falls from rest through a vertical distance h, and there is a vertically upward electric field also. So what are they saying? There is an electric field upward and an electron is dropped from rest to travel a distance h. What will happen during motion? Its weight will act downward, let's say mg, and because electric field is upward, electron will experience an electric force downward, which is E times electric field, the charge times electric field. So total force would be mg plus electrical force EE, and acceleration of electron can be written as total force divided by mass would be g plus EE divided by m. This is the acceleration of electron. But now if, as second condition says, if electric field is reversed and instead of an electron, a proton is dropped. Again the weight will act downward, but weight is much larger for proton, you know, because mass of proton is much larger than mass of electron. So weight will act downward and electric force too will act downward, because we have flipped direction and proton is positive charge. Electric force will too act downward. Now we can write acceleration of proton as again total force by mass, which is g plus EE divided by mm. Now you all know mass of electron is less than mass of proton, and since mass is in the denominator, this mass is less than capital M, so acceleration of electron will be greater than acceleration of proton. So I can say acceleration of electron is greater than acceleration of proton. And since they both have to fall same distance, because of this larger acceleration, obviously the electron will speed up faster than proton, and if it moves faster than proton, it will take a smaller time than proton. So electron will take a smaller time than proton. So correct answer is obviously A. Okay, so that was a simple question. Let's move to next question. See, in this problem they are saying they have projected a charged particle of mass m and charge q from origin towards x-axis, towards positive x-axis. And as the charge leaves origin, it faces an electric field downward. So because of electric field, the charge will experience a push downward because direction of electric field is downward. It will start experiencing a push downward, and the path of particle would be a parabola like this, right? At some point here, the electron will enter this region, and in this region, you know, there is no electric field, and as there is no electric field, there is no force, and because of no force, the electron will move on a straight line like this. If you extend this line, because we have to know the equation of this line, we can do a lot of calculations. But if you observe a little and extend this line back, you all can see this line has negative slope. If you express it in y equals to mx plus c, it will have a negative slope, negative coefficient of x. And let us see, in A, it has positive slope, the line has positive slope. In D, the line has positive slope. In C, the line has positive slope because x has positive coefficient, but only in B, x has negative coefficient. So answer should be B only. There is one more observation. You all can see the line is not passing through origin. So obviously the D and A cannot be true. The correct answer is obviously B. Okay, so let's move further. Next question. In this problem, they are saying a particle of mass m and charge q is released from rest. This is a very simple question. A particle of mass m and charge q is released from rest in a uniform electric field, and if there is no other forces on the particle, there are no other forces on the particle, obviously its initial speed is 0. It will experience an electric force, the charge times electric field, and its acceleration would be QE, the force divided by mass. You all know the charge is constant, the electric field is uniform, means constant, mass is constant, so this acceleration will be constant. And if acceleration is constant, the particles follow laws of motion defined by V equals to U plus AT, S equals to UT plus half AT square. So they are saying they want to know the speed as a function of distance traveled by it. So if you remember the laws, you will write obviously V square equals to U square plus twice AS. Okay, because this equation is applicable when charge moves with constant acceleration. And V square equals to U square. The particle is started from rest, so U is 0 plus twice acceleration is QE divided by M times distance traveled. So V as a function of distance traveled is going to be a square root of 2QE by M times distance traveled S. So like this. Okay, this is a simple parabola, you all know it, and if V is proportional to root S, the shape of parabola would be like this. So correct answer is B. Okay, so let's move a little. I think you are ready for the next problem, so let's start. In this problem, they have three charges, minus 4Q, 2Q, minus 2Q, placed on a circle of radius D, and they want to ask what is electric field at origin. All the positions are clearly specified by the angles you can see, and let us find electric field at origin. Okay. Since all charges contain Q, let us assume, and we have to find the electric field at point O, which is at a distance of d from every charge. Let us assume the field by one charge Q, kq by d square as E. Let us assume field by one charge is E. So, if you want to find field by this minus 4q, field by this minus 4q, so it will be equal to 4E, because field of one charge is E, field of 4q will be 4E, and since it is a negative charge, the field will be towards it. Similarly, the field of minus 2q charge will be towards it. It will be 2E, and field of this 2q will be away from it, means in this direction, and again 2E, because this is also 2q. So 2E and 2E become 4E. So as a whole, we have 4E field in this direction and equal magnitudes 4E field in this direction. If I break these fields into components, right, we will have vertical component 4E sine 60, and we have vertically downward component 4E sine 60. And since they both are equal in opposite direction, they will definitely cancel, and their horizontal component 4E cos 30 and 4E cos 30 are definitely going to add. 4E cos 30 are going to add. So what I can say is net field at origin is going to be twice of, because we have two components 4E cos 30, twice of 4E. E is simply kq divided by d square to 4E cos 30. Cos 30 is root 3 by 2. You put k as 1 upon 4 pi epsilon naught. So you will have root 3 q divided by pi epsilon naught d square. So you can all check the correct answer is A. Okay, let's move to next question. Yes. Again, this is a very interesting question, and it says we have 10 charges. 5 charges plus q and 5 charges minus q. Okay, and they are placed on a circle in a very uniform manner. Let me show you in the next page, and we have to find field and potential at the center of that circle. So I've already drawn the figure, and they are saying they have placed plus q at alternate places, like plus q is here, then next plus q is here, next plus q is here, next plus q is here, and next plus q is here. Okay, and at all vacant places they have placed minus q. Remember, at all vacant places we have minus q. And now we have to calculate electric field and potential at the center. There is one thing they have clearly said: angular separation between all charges is same. Angular separation between all charges is same. Okay, so as you can count, these are 10 charges. Angular separation between any two would be 2 pi by 10, that is pi by 5. So it is pi by 5. Okay. Now let us calculate potential first. Let us suppose the radius is r and potential at the center will be potential because of all these 10 charges. The potential because of one positive charge would be simply k q by radius, and since all positive charge have same potential, or all charges are same, all distances of charges from center are same, so we will have positive charges potential as 5 kq by r, and similarly negative charges potential as minus 5 kq by r. So obviously the potential at center is 0, no doubt about it. Okay, potential at the center is 0. Now let us think of electric field. Okay, so first I'll suggest you to think of electric field by positive charges. If you think of electric field by positive charges, the field of this positive charge will be like this. Call it E. Okay. And field of this positive charge would be like this. You can call it again E. Magnitude will be same because the charge is same, the distance is same. But the angle between these two would be 2 pi by 5. 2 pi divided by 5, as you can easily calculate. Okay. There are two gaps. So one gap's angle is pi by 5. So two gaps angle is 2 pi by 5. Similarly, this positive charges field would be like this. E, its would be like this, and its would be like this. It can easily be seen that all these angles are equal. All these angles are equal and equal to 2 pi by 5, and all these vectors are equal in magnitude. So if you arrange 5 or any number of vectors, any number of equal magnitude vectors, such that they are spaced equally in two dimension. They are spaced equally in two dimension and they are symmetric about origin. They are symmetric about center. Their resultant is 0. So I can simply say the net field by all 5 positive charge will be 0 because they are creating symmetrical electric field at the center. And similarly, the same logic can be applied for negative charges. The same logic can be applied for negative charges. The negative charges also create symmetrical electric field at origin in all directions. So they too will have a net electric field 0. So electric field at center is also 0. So correct answer is, let me check, the correct answer is A, because field is 0 and voltage is 0. Okay. So let's move further. Okay. This is again a very good question and I think you can solve it yourself. So I'll suggest you pause the video, okay, and solve it yourself first and then look at the solution. I am jumping towards the solution directly. Okay. So we have two charges, Q1 and Q2. Okay, you can see that Q1 and Q2 are the two charges placed at A and D. And this is a right angle triangle whose two sides are x1 and x2. Perpendicular and base are x1 and x2. And they are saying the resultant field at the point O is perpendicular to hypotenuse. So what are they saying? The field at O, obviously the Q1's field would be like this. Let's call it E1. Q1's field will be like this, E1, and Q2's field would be like this, let's say E2. Okay. But they are saying the resultant field is perpendicular to hypotenuse. So if resultant field is perpendicular to hypotenuse, I must draw a line parallel to hypotenuse here. Okay. This dotted line is a line parallel to hypotenuse, and if electric field is perpendicular to hypotenuse, the net field should be like this. E net should be like this. And obviously, if I consider this angle as this angle as theta 1, this will be theta 1. Okay, this will be theta 1. You can see these two are alternate angles, theta 1, and this too is theta 1. And similarly, if this is say theta 2, this will be theta 2. And there is a simple condition. If the resultant is along this line, which is perpendicular to hypotenuse, the component along the direction of hypotenuse must be 0. You can see E2 has a component E2 sine theta 1 in the direction of hypotenuse, and E1 too has a component E1 sine theta 2 along the direction of hypotenuse. If electric field is perpendicular to hypotenuse, these two components must cancel. So what I can write is E2 sine theta 1 equals to E1 sine theta 2. Let's write their values. E2 is K times Q2 divided by X2 square. Okay, and what is sine theta 1? See, sine theta 1, this is theta 1. So sine theta 1 is going to be X2 divided by hypotenuse. Let's do one thing. Draw a line like this. This is 90 degree and call this length as D. Okay, I'm calling this length from here to here as D. So sine theta 1 is going to be D divided by x1. Okay, D divided by x1. So sine theta 1 is D divided by x1 equals to E1. E1 you can write as K Q1 divided by x1 square, and sine theta 2. See, sine theta 2 is going to be D divided by x2. D divided by x2. D divided by x2. So I think few things cancels out. K cancels, D cancels, x1 cancels, x2 cancels, and we are left with Q1 divided by Q2. Bring this Q2 here and x1 here equals to x1 by x2. So obviously the ratio Q1 by Q2 is going to be x1 by x2, and the correct answer is D. Now let us learn few more fundamentals of electrostatics. Students, I will recommend you to watch this lecture in steps of 1 hour or 1.5 hours each, so that your learning can improve. Okay, so we have seen electric field and potential produced by point charges. They were actually kq by r square and kq by r. But what if we arrange large number of point charges in a line and it becomes a line charge? So it is a line charge, it's an infinite line charge, or you can say it's a very long line charge having positive charge density lambda. Actually lambda here is charge density, or you can say charge per unit length. Here lambda is charge per unit length, means coulombs per meter. And since charge is distributed in a line, I have expressed it in lambda. Okay, so if you know lambda and it is a positive charge wire, the electric field at any point P at a distance r from the wire is perpendicular to the wire like this, and E is given by 2k lambda by r, where your k is the famous 1 upon 4 pi epsilon naught. Okay, so try remembering this formula. And if the charge is negative, the direction of electric field simply flips. It is towards the wire. Okay, the second case is also very important. It is again an infinite wire, but we are trying to find electric field at one end of the wire, or you can say at a r distance perpendicularly from one end of the wire. It is commonly called as semi-infinite wire because it is infinite in upward direction only, and below this level there is no wire. If this is the case, now we observe electric field has two components. One component of electric field is perpendicular to wire, we are calling it E perpendicular, and one is parallel to wire, you can see it is E parallel. So if there are two components, the net electric field is something like this, and all three things are written here. E perpendicular is given by k lambda by r, E parallel is given by k lambda by r, and resultant electric field, as the two components are equal to each other, the resultant electric field will make 45-degree angle with this perpendicular, or you can say this wire. Okay, so this is the resultant electric field, and the resultant electric field becomes 2k lambda by r. Again, if the charge is negative, just flip the directions. E perpendicular is going to be leftward and E parallel is going to be upward. You have to remember one more case. Here in this case, in the case of large infinite wires, the electric potential is not defined. You cannot define electric potential, though you can calculate potential difference between 2 points. I'll tell you how. Okay, so this is about electric field of infinite wires or long wires. Suppose in some case you are asked to find electric field at the center of a semicircular or some circular arc. Okay, so here I have taken some circular arc. This is its center C, and say arc is making an angle alpha, subtending at an angle alpha at the center. So what we observe is, if charge density on the wire is uniform, means the linear charge density is uniform, the electric field is in the direction of angle bisector of this angle alpha, or you can say in the line of symmetry, along the line of symmetry of the system. So this is the electric field. Okay, this angle is alpha by 2, this angle is alpha by 2, and this E is given by 2k lambda by r sine alpha by 2. Okay, fortunately here you can define potential also, and see, as every one of you can see, every bit of charge is at equal distance from center, and the distance is r. The potential will be actually k total charge divided by r. And what is total charge? The total charge can be written as k lambda. Lambda is charge per unit length. Okay, and multiplied by this length of arc. And you know the length of arc is equal to angle multiplied by radius. So actually angle is alpha and the radius is r. So length becomes r times alpha divided by r. You cancel r. You can put the value of k as 1 upon 4 pi epsilon naught, and it becomes lambda alpha divided by 4 pi epsilon naught. But I won't recommend you to remember this formula. I'll only say you remember V equals to kq by r, and just put the value of q in terms of lambda, if lambda is given to you. Okay, let's move a little. This is again a very important formula. If charge is uniformly distributed over the length of a ring, this is a ring of radius r, and you want to know electric field and potential at a distance of x from the center along the axis of, or along the principal axis of the ring. So if this is the point where you want to find electric field and potential, the electric field is given by this formula and potential is given by simply kq by r. Remember kq by r, where r is this distance. I always recommend to remember these two formula, kqx by r cube, kq by r for electric field and potential, and obviously where r can be represented as r square plus x square to the power 1 by 2. So this becomes this also. Okay, and what if the charge is distributed over the area, uniformly over the area of a circular disk? Now I can define a new charge density, sigma. Sigma is charge per unit area, Coulomb per meter square. So sigma is surface charge density or charge per unit area, and it is distributed uniformly over the disk. Okay, so you pause the video, remember the formula. The electric field is given by this, and potential is given by sigma by 2 epsilon naught r minus x. You can again check, the r is this distance, x is this distance, and here I have written cos theta. So cos theta automatically becomes base upon hypotenuse, that is x by r. So these are the formula for electric field and potential of ring and disk. There is one more thing. If you imagine a very large disk of radius very large as compared to this distance x. So if you make radius to be very large as compared to x, this theta will approach almost 90. And if this theta becomes 90, you put cos 90, and cos 90 would be 0, and electric field will become sigma by 2 epsilon naught only. And this becomes a very large disk. And once the disk is very large, infinitely large, it doesn't make any sense that its shape is circular or rectangular, because the size is so large. So if this is a very large sheet of charge, having uniform surface charge density sigma. It doesn't matter what's the shape, because shape is at infinity. Okay, so if this is very large sheet, do not confuse this with a wire. It is not a wire, because wire would have charge density lambda, charge or unit length lambda. Okay, actually this is the side cross section, side view of a large sheet. That is why we are looking only at the thickness of the large sheet. Okay, so this is the large sheet. If it is positively charged, the electric field is found to be almost uniform in the region, right? And electric field is given by sigma by 2 epsilon naught. Believe me, JEE and NEET both have asked too many questions based on this formula. Okay, so let us move for few questions also. Okay, so we have our first question, and in this question they say there are two parallel infinite line charge having charge density lambda and minus lambda Coulomb per meter, and they are placed at a distance of 2r. So we have two large wires having charge density lambda and minus lambda. The gap between them is 2r, and there is a point in between them at a distance of r from one and also the same distance r from the other, and we have to find electric field at this point. See, electric field at this point will be because of two configurations. So due to this positive charge, electric field is towards right. Let's call it E, and you all know E equals 2k lambda by r. Okay, and now electric field because of this negative charge, will be towards it, and since the charge density has same magnitude, the distance is same, its magnitude will also be E. So net electric field at this point will be 2E. So E net is going to be 2E. Just put the formula 2 multiplied by 2, k is 1 upon 4 pi epsilon naught lambda by r, and you have lambda by pi epsilon naught r. So where is lambda by pi epsilon naught r? You have correct answer as C. Okay, so over to next question. In this question again, I have not included every question, but I remember 3 to 4 questions at least previously asked based on electric field of infinite large sheets. So this time we have two large sheets. Okay, we have two large sheets, both having uniform surface charge density sigma, and they are placed at 30-degree angle with each other. And we have to find electric field somewhere in between the space at this point. Okay, so let's find it out. Okay, let's take a point here. Let's P, and at P, because of this charge, because of say first charge, the electric field is going to be upward like this. Call it E, and E is simply, I think you remember the formula, sigma divided by 2 epsilon naught. Okay, and E is perpendicular to the charge. Okay. Similarly, at this point, the electric field because of this sheet will too be perpendicular to the sheet and along this direction. As the sigma is same and the magnitude is independent of the distance, the magnitude of this field will also be E, that is sigma divided by 2 epsilon naught. Now we have to know the correct electric field. So as we can see, this electric field is in y direction, but let us break this into two components, x and y. So we have one component as this and one component as this. If you use a little geometry, you will easily know this angle is 30, and if this is 30, it is going to be E sine 30. What is sine 30? Sine 30 is 1 by 2. So this component, horizontal component, is E by 2, and this component is going to be E root 3 by 2. Okay, so now we know, let us put the values. The net electric field in x direction is obviously towards left, in the negative x direction. So we have minus E by 2. So E by 2 would be sigma divided by 4 epsilon naught I cap, or in these options they have written x cap. So you can consider x cap as a unit vector along x axis. And in y direction we have E upward and E root 3 by 2 downward. So we have E and 1 minus root 3 by 2 y cap. Y cap you can consider as a unit vector along y direction. So obviously, if you can put value of E, you will easily know what is the resultant electric field. But if you observe it, we have negative x component. Okay, so we have two options A and B with negative x component. Obviously the answer is in between A and B. Okay, and now if you see y component, in y component one term is positive, one term is negative. So you can easily see here in y component both terms are positive, here one term is positive, one term is negative. So correct answer is obviously B. So we can move to next question. Okay, okay. Again, I'll say you same thing which I said earlier. Any question, the moment you see any question, just pause the video, read it carefully, and if you think this question is too easy for you, then you can skip the video. You can skip for a few minutes, maybe one or two, and you can move to next question. But if you find the question difficult for you, or if you want to attempt the question, just pause the video, attempt it yourself first. Okay, if you want to give 2 or 3 attempts, give it 2 or 3 attempts and then see the solution. Okay, so now we have next question. For a uniformly charged ring, we have a uniformly charged ring of radius r. So we have a ring and it is uniformly charged. Let's say charge is q and say the radius is r. They are saying the electric field on the axis has the largest value at a height h from the center. Electric field has a largest value, means maximum value of electric field at a height h from the center. And what is the distance h? Okay, if you remember the formula, the electric field at a height h will be given by E. Okay, E equals K Q. In the place of x we have h divided by x square, not x square, r square plus h square to the power 3 by 2. Now you want to find at what h the electric field is maximum. What we will have to do? We will have to apply maxima and minima of calculus, and we will have to calculate dE by dH. And when it is 0, obviously the field is maximum. Okay, so let us differentiate it, KQ, and you can see in the numerator and in the denominator both have term h. So we will be using quotient rule of differentiation. And if you use quotient rule of differentiation, we have denominators square, r square plus h square की power 3, and in the numerator we will have r square plus h square power 3 by 2, and numerators derivative h derivative, that is 1 minus h, and derivative of denominator. See, if you differentiate the denominator, you will have first 3 by 2. Okay, then you will have r square plus h square to the power 3 by 2 minus 1, that is 1 by 2. and then according to chain rule, you will have to differentiate this term once more. So r square's derivative 0, h square's derivative is 2h. Okay. And when this is 0, electric field will be maximum. So solve a little, and if you just put numerator equals to 0, you will have h as r divided by root 2 as an answer. So the correct answer is B. Correct answer is B. Okay. So now it is time to learn few more fundamentals. Okay. So you must remember electrostatic field, which is produced by static charges, is conservative in nature. And if some field is conservative in nature, its potential energy can be defined. So electrostatic potential energy is defined, and electrostatic potential energy is defined as change of potential energy is actually negative of work done by electrical forces. Or vice versa, you can write work done by electrical forces is equal to negative of change in potential energy. Always remember, work done by electrical forces is equal to negative of change in potential energy. If during some change, or if a configuration changes itself because of some external forces, and they ask you what is the work done by external force. So if the changes in the system are slow, you can always consider there is no change in kinetic energy, and all the work done by external forces goes into increasing the potential energy of the system. So work done by external forces is equal to change in potential energy of the system. Okay, and in many questions I've seen they say only one charge is moving. If only one charge is moving, the change in potential energy can be written as the moving charge multiplied by change in potential difference between the points the charge is moving. So you can write delta U as Q delta V, where delta V is potential difference. Now if you have two charges Q1, Q2 at a separation of R, this system also has some energy. And this energy of this system, or energy of a 2-point charge system, is given by U K Q1 Q2 by R. K Q1 Q2 by R. Okay. Remember, if the charges are positive, they will repel each other. If the charges are negative, both negative, they will repel each other. And in both cases, if the system is repulsive, its potential energy is going to be positive. Okay. But if one is positive, one is negative, potential energy is negative. So attraction, if system has attraction, its potential energy is negative. So how you will get this positive and negative sign? The simple idea is use these charges with their sign. If both are positive, potential energy positive. Both negative, again potential energy positive. But one positive, one negative, you will automatically get U as negative, right? But remember, attraction implies negative potential energy. Repulsion implies positive potential energy. Okay. Next point, if you are given more than two particles. So if you are given more than two particles, try to try to figure out the distinct pairs in that system, and if you add all the energies of these pairs using this formula, you will get complete energy of the system. Okay, so for getting complete energy of a n particle system, you have to add the energy of each pair by this formula, and the only thing is any energy should not repeat. So you have to add energy of distinct pairs, right? Okay, the next point is, I think you know what is equipotential surface. Equipotential surface is an imaginary surface where electric potential is same at all points. So if you move a charge from one point of an equipotential surface to some other point of same equipotential surface, the potential difference is zero. And if potential difference is zero, no work is done by external forces. So always remember this point. If you see some difficult configuration, and if charge is moving from one point to other point, and you just by chance notice the 2 points where charge is moving, the potential is same, simply write the work done is zero. And one very important thing, what is that? If you release the charge, if you release a charge in electric field or a charge configuration in electric field, it may move. If you want to guess the movement, in which direction the configuration is moving, there are two methods. Just look at forces. And by looking at forces, you can easily see the positive charge moves in the direction of field, the negative charge moves in the opposite direction of field. Okay. If you let them go, if you just release them, if you drop them and release, then it will happen. But in terms of energy, every configuration of charge will move in such a way to decrease its potential energy, remember this point. Okay, so that is the last point, and let us solve few more important questions based upon this. Okay, so this was JEE Mains 2019 question, and in this question they say there are three charges, Q plus small q plus small q, and they are placed at a right angled isosceles triangle. If they are placed at right angled isosceles triangle, let's say this distance is L, this is L, and this will automatically be L root 2. And we have to know what is the magnitude of this charge capital Q if the system's energy is 0. So let us write system's energy. As this is not a two charge particle system, it is a three charge particle system, we will have to understand how many pairs are there in this, how many distinct pairs are in this. So the first pair is this, the second pair is this, and the third pair is this. All these pairs are distinct. And how to calculate energy? Just write energy of these three pairs using K, Q1, Q2 by R formula. So energy of first pair is going to be K QQ divided by L plus K QQ, that is Q is square, divided by L plus K QQ divided by root 2L equals to 0. Right? Now you can cancel Q, K and L. Now take Q common, you will have 1 plus 1 by root 2, and take this Q on the right hand side, you will have minus Q. Now transfer few more terms on the right hand side and you will have B as correct answer. Okay, so over to next question. Okay, so what we have here? We have here 4 charges. I again say, just pause the video, attempt it yourself, okay, and then look at solution. So we have 4 charges and all charges are Q each, and they are placed at these coordinates. And if you draw these coordinates on an XY graph, you will notice all these charges are placed at the vertices of a square of side 4 meter. And they are saying what is the work done in bringing a fifth charge Q from infinity to the origin of coordinate system. How to calculate? If I just told you, if you bring one charge from one point to another and the work done is to be calculated, so work done by external agent is given by delta U, which can be written as moving charge multiplied by delta V, means potential difference. Initially the charge was at infinity and finally we are bringing it to origin. So potential at origin minus potential at infinity. You all know we consider potential at infinity to be 0. So the correct answer is Q times potential at origin. Let us write it again. See, if you want to write potential at origin because of these 4 charges, you can see these 2 charges are at equal distance of 2 from origin. So potential because of this at origin would be KQ by 2. Potential because of this 2 will be KQ by 2. So we have 2 terms of KQ by 2. Plus potential because of this. As this is 2, this is 4, this is going to be root 20 by Pythagoras. So potential because of this cube would be KQ divided by root 20, and potential of this will also be same. So we have 2 here and just take K, Q common. We have Q outside. Inside we will have 1 plus 1 over root 5 as an answer. So work done by external force is this. And if you check the options, the correct answer is B. Okay, let's move to next question. You can anytime pause the video, take a break, just look at the question, try to solve it yourself. Okay, you have to don't stress yourself, right? 2-point charges. So we have 2-point charges. One is placed at x equals to minus d by 2 4q, and one is placed at x equals to plus d by 2 minus q. And there is a third charge, point charge q, and it is taken from origin over to point A, which is at x equals to d, along this circular path. And they have asked us what is the change in the energy of the system. So you know the energy, the change in energy of the system is actually equal to minus of work done by electrical forces. And since electrical forces are conservative, it doesn't matter which path the charge takes to go from one point to the point. It is the same. So it doesn't matter you take the charged particle from this path or any random path. We are taking charged particle from origin to point A, right? And the change of energy, I am going to calculate change of energy. If it comes positive, means energy is going to be increased. If it is negative, the energy will decrease. So change of energy would be the traveling charge Q multiplied by potential difference, potential at A minus potential at O. Okay, Q. See, potential at A because of 4Q would be K 4Q divided by, not this Q, 4Q divided by 3D by 2. You can see the distance is 3D by 2 plus potential because of minus Q. Obviously, it would be negative. So, potential because of minus Q would be minus K Q divided by this distance is D by 2. So, this is potential, net potential at A and minus potential at O. Potential at O is because of 4Q. Yes, like this. Because of 4Q at point O, potential is K 4Q divided by D by 2, and potential because of minus Q is minus KQ divided by D by 2. Just calculate this stuff and you will see the change will be negative. And if change is negative, potential energy is going to decrease, and just check the result, you will notice the correct answer would be B, because after calculations your magnitude of change is going to 4Q square by 3 pi epsilon naught D. Okay, so this way you can calculate change in potential energy of the charge. Okay, so I am moving to next question, but if you feel tired, just take a break of 5 minutes and then you can start. Okay, now this is also a very important concept and more important for JEE mains and advanced. The relation between electric field and potential. You know both are electric field. One is a vector electric field, one is a scalar electric field, but there is a relation between them. And what is the relation? Actually, if you differentiate potential in a certain direction, then negative derivative of potential in that direction gives you electric field component along that direction. Never think this will give you the electric field. It will give you the electric field's component in that direction. means minus del V by del X will give you Ex only, minus del V by del Y will give you Ey only, and minus del V by del Z will give you Ez only. Okay. Suppose in some question they say this is electric field, no, this is potential and this is x-axis, and the potential is like this, and the potential is like this. So what is the electric field direction at this point? Just have a look. At this point the slope is positive, dV by dx is positive, and if dV by dx is positive, dV by dx is positive, minus dV by dx is negative, and minus dV by dx is negative means E is negative. So E is negative, electric field is this way. At this point, you can see the slope of curve is negative. So dV by dx is negative. If dV by dx is negative, minus dV by dx is positive, so electric field is positive. Here electric field is positive, here electric field is positive, and at this point, because slope is 0, here we have electric field as 0. So always remember, whenever you see a potentials maxima or potentials minima, the electric field component is 0 there. The electric field component, actually we are talking about electric field's x component, and it is 0 there. It is Ex. From this information we can not say anything about Ey and Ez because we are given only V versus X diagram. Okay, and at this point where the potential is maximum, Ex is 0. From this you can say the component of electric field will always be in the direction of decreasing potential. Can you see that? Here potential is decreasing towards right, so electric field is towards right. Here potential is decreasing towards left, then electric field is towards left. Okay, so always remember this fact. In the direction of electric field, potential always decreases. In the direction of electric field, potential decreases. Actually, if you move along electric field, if you move in the direction of electric field, in that direction potential will decrease at maximum rate. Okay, so we have this very important point: along the direction of electric field, electric potential decreases at maximum rate. And the second point, if you already know the potential in terms of x, y and z, differentiating partially with respect to x, y and z, you can know what is Ex, Ey and Ez, and after these three components you know complete knowledge of electric field vector. But what if you know electric field and they are asking you potential difference? So if you know electric field and they are asking potential difference, this is actually dot. So actually potential difference between points A and B, VA minus VB, is given by E dot dr from A to B. Remember, E dot dr from A to B, path does not matter because electric field is conservative field, and since electric field is conservative, which path you take, it will not matter at all. Okay, so if you are given potential, find electric field using concept 1, and if you know electric field and you want to find potential difference in a region between point A and B, use concept 2. There's one more thing. If in a region potential is constant, if they say in a region potential is constant, remember and listen very carefully. If they say in a region potential is constant, means dV by dx is 0, dV by dy is 0, dV by dz is 0, because in every direction, suppose in this room potential is constant, along x-axis dV by dx is 0, along y-axis dV by dy is 0, along z-axis dV by dz is 0, because potential is constant, there is no derivative. In that case, in this region, in that region where potential is constant, Ex, Ey, Ez all will be 0. So if you have an idea that potential is constant in a region, in that entire region electric field will be 0. Okay, that's a very important concept, will be used in conductors. Okay, so after learning these concepts, let us solve few more questions based upon these facts. Okay, so we have a question, and this was NEET 2020 question, and it says in a certain region of space whose volume is 0.2 meter cube, we have a space of volume 0.2 meter cube, and electric potential is found to be 5 volt. At every point electric potential is 5 volt. Means potential is constant in this region, and if potential is constant in this region, you already know, I just told you, electric field at all points will be 0, and I think they are asking electric field. Whoa, what is the magnitude of electric field in this region? Answer is simply 0 because potential is constant. So dV by dx is 0, dV by dy is 0, dV by dz is 0, ex 0, ey 0, ez 0. So net electric field is simply 0. Over to next question. Not question. Over to next concept of electric dipole. What are dipoles? If a charge configuration has net charge 0, means it has some positive charge and equal negative charge, then this configuration may act as a dipole. The most simple dipole is a pair of charge plus q and minus q placed at separation L. So if this is a dipole, we defined a physical quantity representing this electric dipole, and that quantity is called electric dipole moment. The electric dipole moment's magnitude is q times L. Q is any one charge and L is the gap between them. And remember, the direction of dipole moment is from negative to positive charge. Negative to positive charge. The direction of dipole moment is from negative to positive charge. So means dipole moment is a vector quantity. Dipole moment is a vector quantity. It has all three in it. It has charge in it. It has gap length size in it. And it also has direction, means it has orientation of negative charge and positive charge also included in this physical quantity. So P is defined as QL and the direction of P is from negative to positive charge. But remember, if you have a many charged particle system acting as a dipole, the dipole moment is given by this sum. Summation of Qi Ri vector. It is same as you would have calculated center of mass, in which you do summation of Mi Ri vector. The same way, if you pick all the charges separately and multiply them by individual R vector Qi, like Q1 R1 vector, Q2 R2 vector, and sum them up vectorially, you will get dipole moment of multi-charge particle system. Okay, so this is dipole, but we mainly talk about ideal dipole. What is an ideal dipole? Ideal dipole is a very tiny pair of charge, one positive charge, one negative charge, placed at a very small separation L. Okay, then this is called an ideal or a short dipole. Okay, if you are given a short dipole, it is represented by a arrow P vector here. The arrow shows at the tail we have a negative charge and at the head we have a positive charge. In many questions they ask you what is the field and potential of this dipole, and if they ask you field and potential of this dipole, okay, so just take this dipole as an origin and suppose we want to find field and potential at point P. At point P we want to find field and potential. This point P's position vector with respect to dipole is R vector, and let's say R vector makes an angle theta with P vector. So what we observe at this point, we observe two components of electric field. One is along R, which we call as ER, and remember ER is given by this formula 2 kp cos theta by R cube, and one field is perpendicular to R. This component is perpendicular to R. This component is actually in the direction of increasing theta. That's why we call it E theta, and E theta is kp sin theta by R cube. So resultant field at point P would be vector summation of these two components, and vector summation of these two components give you this result. So this is the general electric field at any point P. Okay. As you can see, the net electric field makes an angle alpha with R vector. You can see with R vector, it makes an angle alpha. So if you just divide or you just take tan alpha as E theta upon ER, you get tan alpha as 1 by 2 tan theta. You can easily do that. That's a very simple calculation. And one more thing, potential at this point P is given by Kp cos theta by R cube. Kp cos theta by R cube. You should remember a few things. If theta is 90, cos theta is 0, so Vp is 0. Means if you are moving on this line or this plane cutting the dipole into equal half, this is called an equatorial plane. And on this entire equatorial plane, the potential is 0 because cos theta is 0. So this is a zero potential equipotential surface. It is a zero potential equipotential surface, right? This is also called equator. This line is called axis of dipole. Okay. If theta is less than 90, remember, if theta is less than 90, cos theta is positive. You must remember, cos theta is positive. Means in this region, means in the half universe where towards the head of the dipole, in this half universe, the potential produced by this dipole is positive. So this region is of positive potential. And when you go to this region where theta becomes more than 90, the potential is negative because cos of angle more than 90 is negative. So you must remember, even along the axis, towards head of the dipole, potential is positive. Towards the tail of the dipole, potential is negative. Okay. One more thing. If you want to find electric field on axis at a distance r from dipole, the electric field on axis is given by simply, you can see this is ER component. This is ER component because this component is in the direction of R. ER component will be 2 Kp cos theta by R cube. Theta is 0, so cos theta is 1. So this electric field on axis, you must remember this. It is a very important result. On the axis of dipole, at a distance r from it, electric field is given by 2 Kp by R cube. Okay. And the E theta component is Kp sin theta by R cube. As theta is 0, sin theta is 0. So we do not have this component. So net electric field on the axis is along R. Simple. Right. Let's move to equator. If you look at equator at a distance r from dipole, let's first try to find ER component. ER means radial component. So at this point, theta is 90, and if theta is 90, cos 90 is 0. So we do not have ER component. We do not have this component. Remove this. Okay. But this component is non-zero. This is E at equator, and E, this is actually E theta component, and since theta is 90, sin 90 is 1, so we have Kp by R cube on the equator. So field at equator is Kp by R cube. Just notice on the axis of dipole, field is in the direction of dipole moment, and on the equator, field is in opposite direction of dipole moment. This is true for these points also. Here also, field will be opposite to the dipole moment, and on these points, electric field will be in the direction of dipole moment. So this is a little bit about field and potential of dipole moment. It will require some time to remember these formula if you haven't learned or remembered till now. So please, if you don't remember these formulas, give it a pause, learn them properly, and then solve questions. Okay. Then we have few simple formula. If I place a dipole in some uniform electric field produced by some other configuration, some other configuration. Okay, so this is electric field, external electric field, and in that electric field I have placed a dipole P, and the P vector makes angle theta with electric field. So what we observe? We observe a torque acts on dipole, and electric torque always tries to align this dipole moment along electric field. Remember this point. If dipole is like this, the torque will try to align it like this. So torque will be clockwise. And if you place dipole like this, the torque will be like this, so that it can make the dipole align along electric field. And the torque is given by in vector the torque is given by P cross E, P vector cross E vector. The magnitude is given by Pe sin theta, where theta is the angle between P and E. So this is the torque acting on the dipole, and potential energy of dipole is given by minus Pe cos theta. Minus Pe cos theta. Okay. One more thing. If theta is 0, torque is 0. You can easily see if theta is 0, sin theta 0, and sin theta 0, then torque 0. And if torque is 0, the dipole is in rotational equilibrium. The dipole is in rotational equilibrium. Obviously, it is in translatory equilibrium too, because one is minus q, one charge is plus q. On one charge, the force is towards right, on other charge, the force is towards left. As the field is same at both points, these two forces are same. So the dipole is in obviously translatory equilibrium. And since torque is also 0, when theta is 0, it is also in rotational equilibrium. Okay, but when theta is 0, this cos theta is 1 and potential energy is least. And if potential energy is least, potential energy is minimum, obviously the rotational equilibrium is an stable equilibrium. Equilibrium. But if you place a dipole like this, field like this, and dipole like this, the angle between dipole and electric field is 180 degree, and if angle is 180 degree, again torque is 0, equilibrium is there, but potential energy is maximum in this case. Pe minus Pe cos 180 will be plus Pe, and plus Pe everybody can see it is the maximum value of potential energy, and in that maximum potential energy the dipole is in unstable equilibrium. So remember these facts, and we will now solve problems asked related to dipoles in NEET and JEE mains. Now let's start with first question on dipole. Here in this question they say we have a short dipole whose dipole moment is 16 times 10 to the power 9 Coulomb meter, and we have to find electric potential because of this dipole at a distance of 60 centimeter from the dipole and on a line making angle 60 degree with the dipole. Means if the dipole is something like this, we want to know potential somewhere here at point P at a distance of 60 centimeter, right, and angle of this line is at 60 degree from the dipole. Okay, so as you now remember, the potential is given by K P cos theta by r square. Put the values as K as 9 times 10 to the power 9, P as 16 times 10 to the power minus 9, cos 60 as 1 by 2, and since this distance is 0.6 meter, so 0.6 meter square is 0.6 square, and you will simply see the correct answer is 200 volt. So your correct option is C. Okay, let's move to next question. Here we have again a dipole moment P, a dipole of moment P, and first It's placed at an angle theta with x-axis like this. Okay. Initially, it is subjected to an electric field along x-axis EI cap. So initially, we have electric field EI cap like this, and the torque is TK cap. So as you know, the torque, the magnitude of torque on a dipole is given by, torque is given by PE sine theta. If we take the angle between P and E to be theta, the torque magnitude tau is equal to P electric field magnitude E and sine theta. This is our first equation. But in second case, where electric field is towards y-axis, root 3e, then it experiences the torque in opposite direction but of same magnitude. You can see T2 is equal to minus T1 vector, means torque has same magnitude. So in the second case, I can write the torque magnitude is again tau, the dipole moment is P, the electric field magnitude is now root 3e, and this time the angle between electric field and dipole moment will be 90 minus theta, because electric field is towards y-axis. So we have sine 90 minus theta as cos theta. Now if you divide these two equations, you will have sine theta divided by root 3 cos theta equals to 1, which will give you tan theta equals to root 3. And if tan theta is root 3, obviously the theta is 60 degree. So correct answer is D. Okay. Next question. This is a very good question, and they are saying we have two dipoles. We have two dipoles. One is minus 4qa I cap and other is minus 2qa I cap. Means the dipoles are directed in the negative x-axis, right? And they are placed on x-axis, and they are saying what is the distance from A? What is the distance from A at which both of them produce the same potential? Both of them produce the same potential. Okay. So let's see how to solve the question. The first dipole is 4qa, magnitude 4qa, and since it is in minus I direction, so we have drawn a negative vector like this towards left. And the second dipole is 2qa, not 4, 2qa, and the distance between them is r. Look, at some point on the left of A, if you check the potential of A, potential of this dipole will be more than potential of this dipole B, because since the dipole at A is larger in magnitude and also at a smaller distance, both these factors will make potential at this point because of dipole at A to be more. So at these points we say the potential of two dipoles cannot be same. If we check some point between A and B, if we check for some point between A and B, see, if we check some point between A and B, the potential of this dipole will be positive, because you know potential towards the head of the dipole is positive and potential towards the tail of the dipole is negative, so potential of A will be negative. So if one potential is positive, one is negative, how can the two potential be same? So this also cancels. Now I'll take some point on this point and say this distance is x. But remember, we have to find distance from A. So in final answer, we have to add r to x. Okay, we have to add r to x. So if I think at this point P, potential because of this dipole and this dipole are same, I can make them same by writing potential because of A as minus k dipole moment 4qa divided by the distance square, means r plus x square, right? R plus x square equals to potential because of this dipole, again negative because in the direction of tail or towards the tail of the dipole, if you go from dipole in the direction of tail, you will get always negative potential. So the potential at this point because of second dipole is going to be k 2qa divided by distance square is x square. This will give you r plus x divided by x as root 2 in magnitude. Okay, so from here you will get r by x equals to root 2 minus 1. So x as r upon root 2 minus 1. But we have to find distance from A. So the correct answer would be distance from A would be r plus x. R plus r divided by root 2 minus 1. So you add these two and you will have root 2r divided by root 2 minus 1. So now you see the correct answer is Delhi or D. Okay, so over to next question. Again, I think you remember the fact I told you a little before that if you release a charge or a charge configuration, it will naturally move in a direction to reduce its potential energy. Okay, and that is a very important fact. Let us see here. Here we see there is an electric field, and since electric field lines are diverging, means the electric field is variable here. And we have placed the dipole. Can you see we have placed a dipole? The direction of dipole is from minus to positive charge, so direction of dipole is towards left. Okay. Now they are saying if I release the dipole, in which direction the dipole will go? In which direction the dipole will go? Let us find potential energy of this dipole. As you know, potential energy of dipole is minus Pe cos theta, and can you see the direction between field and dipole moment is 180 degree. So cos theta is cos 180 and cos 180 is minus 1. So potential energy is going to be positive plus Pe. And since when dipole moves, the dipole moment will not change, only E can change. And you know the dipole will move in such a direction to reduce its potential energy. So potential energy can be reduced only if electric field is reduced. And electric field will be reduced if dipole goes towards right, because you know here electric field is large and here electric field is small. So dipole will try to go in a region of smaller electric field, because there its potential energy will be smaller. So correct answer is dipole will move towards right to reduce its potential energy. So it is moving towards right because its potential energy will decrease. Towards right because potential energy will decrease. So correct answer is Bombay or B. Okay. So over to next question. This is a very easy question. I'm sure you all can do it, but still you pause the video, guess the right answer and then check the solution. They are saying we have a dipole minus q plus q. We have a dipole like this, and there is a charge q which was placed here. This distance is y. It was experiencing a force F. Now if I bring this charge from here to this point where distance reduces to y by 3, what will be new force? What is new force? You know the field at this point, field at equator is actually, Kp by r cube. Kp by r cube. And if this is the field, the force experienced by some charge would be q kp by r cube, and since you have decreased the distance by one third, you have decreased the distance by one third. In fact, you have made the distance one third actually. So if distance, the new distance is one third only, r is initially y, now it is y by 3. If r is now y by 3, the 3 cube will go in the numerator and that will become 27. The force, the field will increase by 27 times. The field will increase to 27 times in fact, and the force will too increase to 27 times. So correct answer is B. Okay. I think you must have guessed this already. So let's move to next question. This is a very tricky question, and if you look for clues, then it is very simple question. Otherwise, some of you may stuck in this question and can pass to next. They are saying we have a dipole whose moment is given, right, and it is placed at the origin. An electric field because of this dipole at this location. We have to find electric field at this location, and in fact we have to guess in what direction electric field is pointing. We have to guess only direction. We don't have to find exact electric field. We have to guess direction of electric field. But they have said something. They have given a clue that the r dot p is 0. Obviously, if you take dot product of p dot r, you will get 0. But they have said it. They have said it, r dot p is 0. If r dot p is 0, means the vector r and dipole moment, they are perpendicular to each other, because only perpendicular vectors have their dot product 0. And if p vector and r vector are perpendicular to each other, the position where we want to find electric field, we want to guess the direction of electric field, is on equator of dipole, right? And if this is equator of dipole, the electric field at this point must be anti-parallel with dipole's direction. So direction of electric field will be opposite to dipole's direction. So if we look at dipole vector, it has negative x component, negative minus 3y component, and plus 2 z component. The electric field will have opposite, flipped direction. So check minus 1, and here we have plus 1, minus 3 plus 3, plus 2k minus 2k. So this is the direction, this is the vector in which electric field is pointing. Okay, so that was a very simple question, but you have to guess, or you have to look for clues. Okay, over to next question. Now they are saying an electric field of 1000 volt per meter is applied to an electric dipole at angle of 45 degree. So there is an electric field of 1000 volts per meter, and dipole is at 45 degree with the field. Dipole moment is given, and they are saying what is the potential energy of dipole. That is a very simple question, because you all know potential energy is minus PE cos theta. Just you have to put some values, minus, what is P? P is 10 to the power minus 29. Electric field is 1000, that is 10 to the power 3, and cos theta is 1 by root 2, cos 45 is 1 by root 2. Always remember 1 by root 2 is nearly 0.7. So if it is nearly 0.7, the option containing factor of 7 should be correct. You just can check the numerical value also, and you will find the correct answer as simply B. So obviously we can move to next question after this. Yes, this is a good question. They are saying there are two identical electric dipoles having dipole moments P1 and P2. P1 is Pi and P2 is minus Pi, means one is placed towards positive x-axis and other is placed towards negative x-axis. And when they are released, means they are set free. They are set free. They can move in any way, any direction. But I said you something. I said if you release a configuration, it will move in such a way to decrease its potential energy. Always remember, to decrease in its potential energy. So since initially they were at some separation and separation was A, and when we release them, they will move. They will either move towards it or away from it, but they will move in a direction to decrease their potential energy. We have to guess in which direction they will move. But question is saying mass of dipole is m. What is their speed when they are at infinite separation? Let us check. Will they go to infinity or not? So I am drawing an x-axis. There is one dipole pi cap pointing in the positive x direction. There is one dipole minus pi cap pointing in negative x direction, and the gap is A. See, if you want to write their interaction energy, their potential energy, the simple method is find electric field because of first dipole at the place of other. So you already remember this is the dipole, this is axis of dipole, and on the axis of dipole I am trying to find field of first dipole at the place of other. Field of first dipole at the place of other. So since the other position is in the axis of dipole, the field is given by 2k p by r cube, and direction of field will be towards right because dipole moment is towards right. Now this field is going to interact with this dipole. This is interacting with this dipole. So potential energy of the system, interaction potential energy of the system will be minus Pe cos theta, right, minus P. Second dipole's magnitude is P. Electric field is 2kP by r cube, and cos theta. You can see the dipole is pointing left, the field is pointing right, so this angle is 180 degree, so cos 180 is minus 1. So can you see 2k p square by r cube? We got positive potential energy. And if we have positive potential energy, this energy will decrease only if the gap between them increases. Actually the gap is A, so I can rewrite this R as A everywhere, A cube. Yes, what I said, as the potential energy is positive, the potential energy will decrease if the charges, if the dipole go away from each other. And you know the natural movement of configuration will occur in such a way to decrease its potential energy, means they will repel each other and they will go away from each other. And if they are going away from each other, obviously after a sufficient time they will be at infinite separation. So if we conserve energy, initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. You know initial kinetic energy is 0 because both were at rest. Initial potential energy we got as 2k p square divided by a cube. Finally, since both are identical, both will be pushed equally, both will gain same speed after same time. So if energy of one is half mv square, energy of two will be twice of half mv square, and when they reach infinite separation, potential energy will be 0. So from here, if you cancel these two, you will get v square as I think 2k p by ma cube, and 2k p square by ma cube is square root and put the value of k is 1 upon 4 pi epsilon naught. I am sure you will get some correct option. And yes, I think we have 2 in the numerator. K will have 1 upon 4 pi epsilon naught. So a 1 by 2 will appear inside the square root. So P by A, we can take A outside. So I think yes, it is the right answer. P square outside the square root, P, A cube, take A square outside the square root, we get A and 1A left in that. So correct answer is C. Okay. So did you get the right answer? Yes. Now let's review it a little, because I think this is a good question. What they had done, they put 2 dipoles, one pointing towards right, one pointing towards left at a separation A. What I did, if they are left to move freely, they will obviously move in such a direction to decrease their potential energy. So I am trying to find their interaction potential energy, right? Their interaction potential energy can be found by where this dipole is standing. This dipole is in the field of this dipole, and this dipole is in the field of this dipole. So what I did, I found field of first dipole at the place of second, and then interaction energy would be minus P cos theta. Okay, this P is second dipole's dipole moment. Electric field is produced by the first dipole, right? Okay, only then it will interact, because it cannot interact with its own field. It can interact with some other electric field. And you can see the P is towards left, E is towards right. So angle between them is 180 degree. So cos theta is minus 1. So we got positive potential energy. And positive potential energy can only decrease if A increases, because A is in denominator. So A increases, potential decreases. Obviously, systems move in such a direction to decrease potential energy. So that is only possible when they move apart. So definitely they will repel. If they repel, they move under electrostatic forces. Electrostatic forces are conservative, potential energy is defined. So systems mechanical energy will remain conserved. If mechanical energy is conserved, I have made Ki plus Ui, initial kinetic energy plus potential energy, equals to final kinetic energy plus potential energy, and we got the result. Have magnitude Q times field at the place of minus Q, and the field of at the place of minus Q is 2K lambda divided by R2, where R2 is 12 mm. Okay. Now you can take Q 2K lambda common, and we will have 1 by 10 mm. I can write in SI units as 1000 by 10, so it will be in meters, minus 1000 divided by 12. Just put the values. The force is 4 Newton equals to Q 2, K is 9 times 10 to the power 9, lambda is 3 times 10 to the power minus 6, and we have over here 10 to the power 3 times 2 divided by 120 by taking LCM. And finally you will have your charge Q as, okay, this 4 is cancelled by 2 and 2, right? The 3 is cancelled by 120, and we will have 40 here. We have 10 to the power 9, we have 10 to the power 3, so it will be 10 to the power 12 minus 10 to the power 6. So we will be having 9 divided by 40 like this. 1 equals to 9 divided by 40 Q times 10 to the power 6. So Q will be equal to 40 divided by 9 multiplied by 10 to the power minus 6, or 40 by 9 is nearly 4.44, and 10 to the power minus 6 is micro, so it is micro Coulomb. So the correct answer is 4.44 micro Coulomb. So answer is D. Okay, let's move to next question. Okay. Keep studying, keep revising. And here we have two ideal electric dipole. Again from a question from 2021. We have two dipoles. One is placed along x-axis. This dipole is P1. And one is placed along y-axis pointing downward, because you know the direction of dipole moment is from negative to positive charge. So dipole is downward, P2. Okay. And they are saying at a point C, the net field by this system of dipole is at 37 degree with the x-axis. So let us check. Okay. As we have two dipoles, you can see the point C is on the axis of first dipole P1. So you know on the axis of dipole, the field is 2 kp by r cube. 2 kp by r cube. As the P is P1, we have 2k P1 by r cube, where r is the distance between O and C. Now, we have one more dipole P2 pointing downward, and this point C is on its equator. For P2, point C is on its equator. And you know on equator, the field is in opposite direction to dipole moment. So dipole moment is downward, so field will be upward. And on equator, the formula for field is Kp by r cube. The dipole is P2, so we have Kp2 by r cube. And the resultant field will be the resultant of these two components. And now we know the resultant makes angle 37 with x-axis. So definitely you can write tan 37 as this component divided by this horizontal component. Let us write tan 37 equals vertical component K P2 divided by r cube divided by 2k, horizontal component 2k P1 divided by r cube. R cube got cancelled, k got cancelled, and we are left with P2 divided by 2 P1. And you already know tan 37 is simply 3 by 4. So you cancel this 2 and you will have P1 by P2 as 2 by 3. So correct answer is 2 by 3, and we have 2 by 3 in option C. So correct answer is C. Okay. So let's move a little and let's see what we have next. So students, we have few more fundamentals in electrostatics, and one is electric flux, and on flux we have Gauss's law. I hope you all know what the electric flux is. When some electric field is passing through an area, this is electric field lines, and when these field lines passing through an area, we say the flux, the electric flux is crossing the area, and the electric flux is given by simply the multiplication of area vector and electric field. So let us see what is electric flux. Actually, when some electric field crosses some area, let us say this is the area, then we say flux is crossing the area. Okay, flux is crossing the area. And actually the area is taken a vector in this chapter. Okay, so the area vector is defined as A vector, and you must know the direction of area vector is perpendicular to the surface. So if this is the surface, area vector is perpendicular to the surface. Let us take electric field vector and area vector are at angle theta with respect to each other. Okay. So if electric field is uniform over the area, the flux is defined as E dot delta A, or E area area cos theta, okay, where theta is the angle between electric field vector and area vector, or simply E dot delta A. Delta A is the area. And if over the area electric field is variable, either in magnitude or direction, electric field is variable, we have to use integral of E dot dA for calculation of electric flux. Okay, there is one very important law about flux, and that law is, if we calculate the electric flux through a closed surface, the closed surface is also called Gaussian surface. So if we calculate electric flux through a closed surface, it will be written as integral E dot dA with a little round here that represents we are calculating flux through a closed surface. What we see, the flux through a closed surface is equal to Q enclosed by epsilon naught. What is Q enclosed? Q enclosed is the net charge enclosed by the surface. So if we have some charges inside like Q enclosed, and if we have some charges outside like Q out, the magic of this law is the flux of electric field through this closed surface. The electric field is produced by both the charges, but the flux depends upon charges enclosed by the surface only, divided by permittivity of free space. So that is the Gauss law. I think you all remember this. Okay, so let us solve few problems based on this. Okay, so that's the 2020 question, and they say in Gauss law, we have seen the statement of Gauss law is this, but they are saying, can we use this type of law for calculation of field, and field equals to Q enclosed by epsilon naught A? Is this applicable? So they are saying, if this equation is applicable, in what situation we can use this equation or this type of equation for calculation of electric field. Okay, so in first they have said only when Gaussian surface is an equipotential surface. In the second they say only when Gaussian surface is equipotential, and also electric field must have same magnitude everywhere on the surface. In third they say electric field has constant magnitude, and in D they say for any kind of Gaussian surface. Obviously D is wrong because we cannot use this type of formula everywhere, because if this would have been the case, why we had studied this complicated one. Okay, so we have two conditions. First is the Gaussian surface must be equipotential. The second is at every point of Gaussian surface we have same magnitude of electric field. We have to check both are important or only one is important. Okay, so let us check. Suppose I take a Gaussian surface like this, enclosing some charge Q, okay, and let us calculate the flux through this, which is E dot dA. Okay, if the Gaussian surface is an equipotential surface, you know electric field is always perpendicular to the surface. Electric field is always perpendicular to the surface. And if electric field is perpendicular to the surface, area vector is also perpendicular to the surface, you can say the angle between E and dA is always 0. And if angle between E dot dA is always 0, this can be written as E dA cos 0, and cos 0 is 1. So we can say it is E dA. But you know it is not sufficient for the formula given in question. So if we take second condition also, and let us assume the electric field has constant magnitude over every point on the Gaussian surface. So if electric field has constant magnitude, this is magnitude of electric field. I can take this magnitude outside the integration sign, and if E is taken outside the integration sign, E will be outside and integral of dA will be total area A. So flux through Gaussian surface becomes EA, and it is equal to Q enclosed divided by epsilon naught. So we can say E equals to Q enclosed by epsilon naught A, and the formula they gave us in the question is valid. So obviously we have used two conditions. Firstly, the first condition is the Gaussian surface must be equipotential, because that is why electric field is perpendicular at every point on the surface. Okay, so Gaussian surface must be equipotential, and the second condition is Gaussian surface, at every point of Gaussian surface electric field must have same magnitude. That is why we can take E outside. Okay, so there are two conditions. So we can say the correct option is C. The surface should be equipotential, and also the electric field must have same magnitude at each point of the surface. So correct answer is C. Okay, let us move over to next question. We have next question, and yes, the next question is actually related to the previous question. How? They say the electric field in a certain region is radially outward and is given by E equals to AR. Okay, so electric field in a region is radially outward. We have this kind of electric field. Okay, the electric field is actually E equals to AR, right? They are saying a charge contained in a sphere of radius A centered at origin will be given by. So we have to take a sphere of radius say A, and we want to know what is charge inside this sphere. So let me take this sphere as a Gaussian surface. If you take this sphere as a Gaussian surface, you can notice that electric field is perpendicular to the surface at every point, because this is a sphere centered at origin and electric field is radially outward. So electric field is perpendicular at each point of the surface, means crossing this surface normally. And this is, from this condition you can say this surface is equipotential. Okay, so this surface is equipotential. Second condition. What is the second condition? Electric field has same magnitude at each point, because the formula for electric field is E equals to A times small r, and small r equals the radius of the sphere, and which is A. Okay, so magnitude of electric field at each point would be capital A times small a. Okay, because the value of small r becomes A. Okay, so we can see the electric field's magnitude is also the same, and if electric field's magnitude is same, if this Gaussian surface is equipotential, I can use the formula they gave us in previous question, which is electric field times area equals Q enclosed divided by epsilon naught. Let's see what is Q enclosed. Q enclosed is the electric field. Electric field is constant A times radius small a. The area of the sphere is 4 pi radius square, 4 pi radius square, and then is epsilon naught. So Q enclosed is this. Let us see which option is correct. Okay, so we have 4 pi epsilon naught A small a cube. Actually this radius is small a, so it becomes small a cube. So correct answer is A. Okay, I hope you understand this question. Okay, and let's move over to next question. Here they say we have a cube and the side of the cube is 0.5, and in this region there exists an electric field pointing along y direction, because we have j cap in electric field, and electric field is variable. Electric field is variable, it is depending upon y coordinate, right? So we have upward electric field like this. and they are asking us what is the charge enclosed. Yes, they are asking us the charge inside the cube. Okay, so if we want to calculate the charge inside the cube, let us apply Gauss law for this cube. You all can see this cube contains 4 vertical walls. This vertical wall and this vertical wall, a backside vertical wall and a front side vertical wall. As electric field is also vertical, it is along y-axis. I am saying y-axis as vertical. The electric field is going to graze these 4 vertical walls, and through these 4 vertical walls there will not be any flux associated. Okay, so through this 4 vertical wall there is no flux. Okay, now let us see flux through this bottom. This bottom is in xz plane. Can you see that? This bottom is in xz plane, and in xz plane the y coordinate is 0. And if in xz plane y coordinate is 0, electric field depends upon y coordinate. So electric field at this plane is 0. So if electric field is also 0, what I can say? I can say the flux through this bottom is also 0. So we have proved through the 5 walls of the cube there is no flux. 4 vertical walls, no flux. Bottom floor, no flux. The flux will be through the top surface only. And at top surface, you know, the value of y coordinate is 0.5, means the height of the cube. So at this point, electric field, at this point on the surface, electric field is going to be 150 times y square, and y equals to 0.5. So we have 0.5 square volt per meter. This is the electric field at the top surface. And you can notice at each point of the top surface, y coordinate has same value. So electric field is uniform also. So if we calculate flux through cube, the flux through cube becomes flux through top surface, because flux is 0 through all other 5 surfaces, and flux through top surface becomes the electric field magnitude, which is 150 times 0.5 square multiplied by area of top surface, and area of top surface is again 0.5 square. This is the flux. And this flux equals, let us see what is the flux. This flux is, I think, 150 divided by 16, and this flux is equal to Q divided by epsilon naught. Q divided by epsilon naught. Okay. As we all know, the value of epsilon naught is nearly 8.6 times 10 to the power minus 12. Okay. If it is 8.6 times 10 to the power minus 12, and this factor is, you can see this factor is nearly 10, a little less than 10. Okay, if it is a little less than 10, the answer should be very close to 8.3 into 10 to the power minus 11. So you can calculate also, and you will find this answer. Okay, so the correct answer is option number B. So we solved this in the previous slide even. We can move to next question. In this question, I'll suggest again to you solve all these questions yourself and then jump into solutions. Okay. So now we have a face, a square face or a square sheet of side A cross A. And exactly above the centroid of this square sheet, we have a charge at a height of A by 2. Okay, we have a charge at A by 2, and they are asking us what is the flux crossing this surface. This question is a little bit tricky one, and it is you can see it is being asked twice in JEE mains. Okay, so let us solve this. Just think, we have 5 more surfaces like this. We have 5 more surfaces like the square sheet we have given in the question. Let us place one sheet like a wall here, another sheet like a wall on this side, one here and one behind, and one over the top. Okay, so we have a closed cube. We have a closed cube, okay, of side length A, and this closed cube encloses the charge completely. As this closed cube encloses the charge completely, so we can say the flux through cube is going to be charge enclosed divided by epsilon naught. So flux through this cube is Q by epsilon naught. Okay. But can you see this charge is exactly in the exact middle of the cube. So with respect to the lower sheet, it is at A by 2 height. With respect to upper sheet, it is again at a distance of A by 2. With respect to this sheet and the front sheet and back sheet, the charge has same location with respect to all 6 faces. The charge has same orientation or location with respect to all 6 faces. So you can say the total flux coming out of the cube is divided into 6 parts equally. And if it is divided into 6 parts equally, the flux through the bottom would be flux through the bottom surface would be Q divided by 6 epsilon naught, because charge is symmetrically at the middle, so charge will be emitting flux in all directions equally. So all the faces, all the walls of the cube will share equal flux. So we have to find flux through this bottom only. So flux through this bottom will be 1/6 of the total flux being emitted by the charge. Okay. So that's the question. We can move to next question now. In this question, they say the charge is distributed. It is not a flux question or Gauss law question. It is a general question, you can say, and a very fundamental also. They say a charge is distributed within a spherical region of radius capital R, right? And the charge density rho R, is depending upon the distance r small r from the center as this function a by r square e to the power minus 2r by a and small a are constants. Okay, what we have to find? We have to find total charge bounded by that sphere. Okay, so let us solve this question. Suppose this is the sphere of radius r, and as they say, the charge density as a function of r is a by r square and e to the power minus 2r by a. So we have variable charge density in this region. Okay, if we have variable charge density in this region, but since charge is spherically symmetric. Why charge is spherically symmetric? Because you can see, if you take a circle of radius x, at every point of this circle, the distance from center is x, so same. And if distance from center is x, we can place r as x, and we can see the charge density over this circle will be uniform. And if charge density over this circle is uniform, I can say charge is non-uniform. Yes, charge is non-uniform in this region, but it is spherically symmetric. Okay, so I'll take a thin shell of radius x and thickness dx. thickness dx. As x increases, the charge density increases or changes, I must say. As x increases, the charge density increases, right? Okay. But actually I have taken x in place of a small r. So you can think x and a small r are same, okay. So if you say we have to calculate charge on this element, charge on this thin shell, what I can say is, as the thickness is very small, I can assume this charge density to be uniform over this shell. And if charge density is uniform over this shell, I can write charge density as rho equals to dq by dv, and dq would be rho times dv. dv is the volume of elemental shell, and volume of elemental shell is given by 4 pi x square dx. I can put value of rho, and value of rho is a by r. You can see the radius of this shell is x, so radius of shell is x, so x square, and e to the power minus 2x by small a, and 4 pi x square dx. You got x square cancelled. And if you want to know total charge within the sphere, we will have to integrate it for the entire volume of the sphere. And you can see the x will change from 0 to capital R, because the maximum radius of the biggest shell is capital R. Okay. So let us integrate this. We have a 4 pi. After integration, we will have minus 2 by a in the denominator, and e to the power minus 2 x by a, like this, from 0 to r. Okay, let us put the values. We have minus 2 pi a, and in the bracket we have e to the power minus 2r by a minus e to the power 0, and which is 1. So this is 1, and this is the total charge. Okay, let us see what they are asking. Actually, they have given the total charge. They have given the total charge, and they are asking us what is the radius r. So we have to find the radius r. Okay, so for finding the radius r, okay, I'll have to bring this on the left hand side. Okay, 1 on the left hand side. Okay, so let us rewrite it. We have minus q by 2 pi a. This was a lengthy question they asked, and e to the power minus 2r by a minus 1. I can bring on the left, we have plus 1, and then we can take log. But before taking log, I can write e to the power plus 2r by a equals to 1 divided by 1 minus q by 2 pi a. Yes, and let's take log. We have 2r by a equals ln 1 upon 1 minus q upon 2 pi a. Okay, and bring this 2 by a on the right hand side. You will have a by 2. So let's see, did we get the correct answer? So correct answer is r equals a by 2 ln 1 upon 1 minus q by 2 pi a. Let us check. Yes, I think we got the answer, and the correct answer is D. Okay, so that was a question. So in this question, they say we have an infinitely long line charge having charge density, uniform charge density lambda, and this line charge pierces a spherical surface like this. Okay, so what they are asking us electric flux through the shell. So in two options they are asking us electric flux to the shell, and in B and D they are asking us what is the type of electric field at the surface of the shell. So let us check. Okay, you know, if you want to find flux through a closed surface, this sphere is a closed surface, the flux is equal to Q enclosed by epsilon naught. So we have to know what is the charge enclosed by this Gaussian surface or this spherical surface. Okay, so suppose this is the line charge. You can see the situation. This is the sphere through which we have to find flux. So let us write Gauss law, and Gauss law says flux through the closed surface equals Q enclosed divided by epsilon naught. As all of you can notice, we have some part of wire trapped inside the spherical surface. You can see this is the length of the wire trapped inside the spherical surface, and let's say the length trapped inside the sphere is L. Okay. If I draw a perpendicular from center to the wire, you can easily see this angle will be 60 degree and this angle will also be 60 degree. And if this is the radius R, this length is going to be R sine 60 through some basic trigonometry, and this length too is going to be R sine 60 degree. So R sine 60 degree, the L is going to be 2R sine 60 degree. L is going to be 2R sine 60 degree. What is sine 60? It is, I think, root 3 by 2. So 2 got cancelled. We have L as R root 2. So if we again write flux will be equal to Q enclosed. You can see the L length of the wire is trapped. So charge of length L will be lambda times L, and L is, this is not root 2, I think, this is root 3, yes, because sine 60 is root 3 by 2, 2 got cancelled. So we have charge inside the sphere as lambda L, and L at the place of L we can write R root 3 divided by epsilon naught. So this is the flux associated with this spherical surface. Okay. The second thing, you know, the electric field of wire is actually perpendicular to the wire. So on the right, the electric field lines will be like this. On the left, electric field lines will be like this. And since wire is along z-axis, can you see wire is parallel to z-axis and electric field lines are perpendicular to the wire, so they are perpendicular to z-axis also. And if electric field lines are everywhere perpendicular to z-axis, the electric field will have no component along z-axis at any place of the sphere. So the first thing is the flux through the shell is root 3R lambda epsilon naught. This we got correct. Okay. And Z component of electric field is 0 at all points on the surface of the cell. This option also is correct because we know the electric field will be perpendicular to Z axis. It cannot have Z component of electric field. Okay. So let's move over to next concept, next very important concept. I have seen many questions in NEET and JEE which are asked based on the field and potential of spherical shells or solid spheres. Okay. So if you have a charge configuration where the charge is uniformly distributed over the surface of the sphere, means we have like painted the surface of a sphere by some charged liquid. So charge will be on the surface only, and this I'll say a hollow charge like football. We have charge on the surface only. Okay. So if we have Q charge on the surface distributed uniformly on this entire surface area, then the shell will be called hollow, the charge will be called hollow. And what we notice when distance from center is less than capital R. What is capital R? The radius of shell, right? And when the point of observation is at a distance small r from center and small r is less than capital R, means point of observation is inside the shell, the field is zero. There is no electric field inside the shell. Okay, there is no electric field inside the shell. And if you find electric field outside it, means R, distance from center is more than capital R, the radius of the shell, the electric field is kq by r square. If you look closely at kq by r square, you will notice that it is simply the electric field of q charge placed at center. Means if you want to know the electric field outside uniform spherical charge shell, you can assume the entire charge of the shell at the center and find electric field just like point charge. Okay, so always remember, if you have a uniform shell, the electric field is zero inside and electric field outside is similar to the electric field of a point charge placed at center of the shell. When we talk about potential, the potential outside the shell is kq by r. So for calculation of potential also, you can assume the charge is center, the whole charge is center at origin. Okay, so if potential outside the shell is kq by r, potential on the shell will be kq by capital R. Okay, because on the shell you can say the distance is capital R. So if potential on the surface is capital R, potential on the surface is kq by capital R. Now if you enter inside, potential will not change, because in a region of zero electric field, potential is constant. So if potential at the surface is kq by r and inside the shell potential is not changing, we have potential at all points inside equal to potential on the surface, which is kq by capital R. Okay, so remember, this is a very important point, very crucial point. If you are inside a hollow shell, uniformly charged hollow shell, the field is zero throughout inside the shell and potential is constant equal to kq by radius of the shell. When you are outside the shell, means distance from center is more than the radius of the shell, the electric field and the potential can be calculated as if entire charge of the shell is centered at the origin or the center of the shell. Okay, so that's the case of hollow charge. But what if the charge q is distributed uniformly over the entire volume? Like you suppose the sphere is a little spongy, and if you dip this sphere into some liquid, into some charged liquid, this sponge will absorb liquid into its entire volume. So the charge will present at the center also, at every volume and every bit of volume of the sphere. So what we say the charge is distributed not only on the surface, it is also inside the surface. Throughout the volume, charge is distributed uniformly. If this is the case and you want to find electric field and potential outside the shell, means distance from center more than capital R. Again, you can imagine the entire charge to be centered at origin O or center of the shell. Simply, as we assumed it in the case of hollow shell, you have same assumption here also. Assume entire charge at center and find field and potential outside shell as if it is a point charge present at the center. Right? But what about inside points? If you want to know potential and field at a point P and it is inside the volume at a distance r from center and r is less than the radius of the shell. Okay, The field is given by this formula, kq by r cube small r. Kq by r cube is small r. Can you see the field is linearly varying with small r? So if you put r equals to 0, field is 0. So field is 0 at center only. At the place of center or at the center field is 0. Then it increases linearly up to the radius r, means from center to surface the electric field increases linearly, and then after that electric field decreases. Okay. So this is about electric field. And about potential. Potential has got a very difficult formula to remember, but if you want you can remember this formula. This is the formula for potential at this point, which is at a distance of a small r from the center, and small r is less than capital R. The potential is given by this formula. But there is one result you can remember. If you put small r equals to 0, small r equals to 0 means you are trying to find potential at the center. Then the potential becomes 3 by 2 kq by r. 3 by 2 kq by r means 1.5 times of the potential at the surface. So at the center of solid sphere, uniformly charged solid sphere, the potential at the center is 1.5 times of potential at the surface. So we can have a little idea about the variations of field and potential also. If we plot electric field versus distance from center, small r, you know up from center, suppose this is the center of the shell, up to distance r, the field is 0. Up to distance r, the field is 0. And then at the surface field is maximum, and then it decays according to kq by r square. This is the variation of field. You see, can you see? It is a very good example of discontinuous function. At this position we have discontinuity. Okay. Let's look at potential. From center of shell up to radius r, we have constant potential equal to k q by capital R. And then potential decreases as kq by small r. So we have potential like this. When we come to solid sphere, your electric field is 0 at the center of the shell, and then it increases linearly up to surface of the shell, and then from here it decreases as kq by r square, because outside the shell the formula for field is kq by small r square. Okay. And now for potential. I am drawing a very small diagram. Look carefully. Yes. As you know, potential outside is kq by small r. Sorry, it is not visible, I think. Let me write it as kq by small r. Okay. So outside the sphere, outside the charged sphere, the potential is simply kq by small r, like this. Potential at surface is kq by capital R. This is V versus R. But when you enter inside surface, potential increases, because inside shell there is electric field, and if there is electric field, potential will change. So potential further increases, and potential is maximum at the center. Potential is maximum at the center, and at this point center, the potential is 1.5 times of kq by capital R. Okay, so this is the variation of potential and distance from the center of a sphere. Okay, so learn this table first and then solve questions I am going to show you further. Okay, But before jumping to questions, let me tell you one very important result. If I have a uniform volume charge density, uniform volume charge, and let's say the charge density is rho. Rho is actually volume charge density. Rho means total charge upon volume. So if we have a uniform volume charge density rho, and through this sphere, in this sphere, a spherical cavity is removed. A spherical cavity is made. So this is a spherical cavity. We have charge everywhere, but we do not have any charge here. Let's say the center of cavity is located at a position vector L with respect to center of bigger sphere, center of charged sphere. Okay, so this center of cavity as a position vector of L with respect to center of charged sphere. Then what we notice after a little mathematics, you can find the electric field in this spherical cavity is uniform. It's a very magical result, but electric field inside this spherical cavity is uniform, and the field is along this vector L like this. Field is along this vector, this position vector like L, like this, and field is given by rho, the volume charge density, then L vector by 3 epsilon naught. So this is the result you should remember. The field is, the first point is field is uniform. The second point is field is along this L vector if charge is positive. If charge is negative, field is opposite to L vector. Simply. Okay. But it will be parallel or anti-parallel with L vector. Right. Okay. And the formula for field is rho L by 3 epsilon naught. Rho L by 3 epsilon naught. So please remember this. Okay. I remember maybe 6 or 7 years back, they asked a question and this answer was simply this: the field is parallel to L vector. The field is parallel to L vector. So this was a question asked in JEE mains someday. Okay. Okay. So now we know the electric field inside a cavity. Okay. So next. Okay. Let's move to next question. In this question, they are asking a hollow metal sphere of radius r is uniformly charged. A hollow metal sphere is uniformly charged. The electric field due to the sphere at a distance r from the center. I just told you, if you have a hollow shell uniformly charged, the electric field up to the surface is 0. Up to the surface is 0. Then at the surface it is maximum, and then it decreases as 1 over r square. Okay, so this is the variation of electric field. Let us read the options. The A option says increases as r increases for r less than r. Definitely it is wrong, because you see, as if r is less than r and r increases, the electric field is constant and 0. So it is not increasing. The next option says 0 as r increases for less than r. This is correct, because from here to here, you see electric field is 0, and after this, when r is more than capital R, electric field is decreases. So in this option, they are saying decreases as r increases for r more than r. So this B option is correct. No problem about this. Okay. Next question. Here in this question, asked in same year in JEE and NEET, here they say, we have a graph of unknown quantity. This quantity may be an electric field or may be a potential, as we can see in the options. This may be a electric field or potential, but the graph is like this. If you just check all the graph of field and potential for solid and hollow sphere, we know the graph, we can see the graph given that question is like this. And if the graph is like this, the variation is of potential. Variation is of potential for a hollow uniform charge shell. So in the question we have potential of a uniformly charged spherical shell. So B option is correct. Right, Bacho? Okay. We can move to next question. Okay. This is a very good question, and it says now we have two concentric spherical shells of radius r and r having charges q1 and q2. So what is the potential difference on the surfaces of two shells? Means we have to find Vr minus V4r, means at the surface of shell of radius r minus potential at the surface of shell of radius 4r. Okay, let us solve it. So suppose we have a shell of radius r and another shell of radius 4r. One is having charge q1 and other is having charge q2, right? Now we want to know potential difference between these 2 points 1 and 2, because this is r and this one is 4r. So potential difference between 1 and 2, v1 minus v2, is going to be integral of E dot dr from 1 to 2. Notice if you go from 1 to 2, you are inside the shell of radius 4r. And if you are inside the shell of radius 4r, field at these points is 0 due to q2. The field is not 0 because of q1. There exists field between 1 and 2 because of q1, but field because of q2 is 0 because these points are inside q2. And if field because of q2 is 0, potential difference will depend upon field of q1 only. And if this field is due to q1 only, potential difference between two shells depends upon inside charge only. This is a very important result you can remember. Okay. So let us find potential difference V1 minus V2, and now you know potential difference is because of Q1 only. Q2 will have no effect. Okay. So because of Q1, potential at the surface of radius R, at the surface of shell of radius R will be K Q1 by R minus at the surface of shell of radius 4r we have K Q1 divided by 4r. You put the value of K, take LCM, and you will have K Q1 divided by 16 epsilon naught pi R. No, not this. We have put the value of K, so you will have 3 Q1 divided by 16 pi epsilon naught R and 3 Q1 upon 16 pi epsilon naught R. So we have answer as C. Okay, bacho. So let's move to next question. Okay. Yes, this is a very good question. And in this question, they say it will involve some calculations. Okay, so be ready for that. Okay, they say we have a region bounded by two shells of radii A and B, and this region is filled with a charge having non-uniform charge density A by R. Having non-uniform charge density A by R. Okay, so here we have charge, but the density of charge is non-uniform. A by R means the charge density decreases as R increases. Okay, the charge density is variable. And at the center we have a charge Q. And they are asking us find the value of A, a constant A, such that electric field in this region is constant. Okay, electric field in this region between shell is constant. Okay, so let us solve this question. To solve this question, I have taken a Gaussian surface by this, shown by this dotted line, and this Gaussian surface has radius say R. This Gaussian surface will include some of the variable charge, variable density charge, and this charge at center. So if you want to find electric field at this point, the electric field at this point can be written as K Q enclosed divided by R square, and see what is the charge enclosed. So you can see This is the charge enclosed. This is enclosed charge, and the Gaussian surface also encloses some charge of variable density, because it also encloses some charge of variable density. Okay, so let this charge is Q dash. It also encloses Q dash. Now our purpose is to find Q dash first. Okay, so for finding Q dash, few minutes earlier I solved a question where we found total charge enclosed in a surface of variable charge density. Here also we will apply same approach, and Q dash would be integral of charge density, which is A by R, times dV, charge density times dV, and dV can be written as 4 by 4 pi r square dr, because this is the volume of elemental shell, and we will integrate it from A to R, because this charge, this enclosed charge, is contained between A and R. This is A and this is R. So from A to R. Cancel this R and you will have, let's see what we have. We have 4 pi A R square minus A square. Okay, now I'll put this Q dash at this point. Let us write E as K Q by R square plus obviously Q dash by R square. So Q dash by R square will have 4 pi A R square by R square 1 minus A square by R square. Okay. Now I'll rewrite this equation into two parts, a constant part and a variable part. So I have constant part as 4 pi A and a variable part as plus 1 over R square. I'll take constant 1 over R square. Yes, because this has Q by R square. So Q and minus 4 pi A square. Can you see that? Yes. This is the electric field. And they said, what is the value of A? What is the value of A if this electric field is constant? So if this electric field has to be constant, obviously this factor should be 0, because if this factor is 0, this term would be 0 and electric field will be constant. And if this factor is 0, you will instantly know what is the value of A. Make this factor 0 and you will know, if you could put E equals to 0, you will know A equals to Q by 4 pi small a square. Q by 4 pi small a square. So let us see which is the right answer. I think there is some mistake. Oh yeah, here we have by 2 also. After integration we will have R dr's integration as R square by 2, and after putting limits we have 1 by 2 also. So cancelling this 2, we will have 2 here, 2 here and 2 here. Okay, and if we have 2 here, after putting this factor as 0, this factor as 0, you will have A equals Q divided by 2 pi A square. So correct answer is Delhi or D. Let's move to our next question. Okay, this question also is very important and asked twice in JEE mains, in 19 and in 20. They made a slight variation in next year, but we will see what. They are saying the charge Q, they had charge Q and they distributed this charge Q over 3 shells of radii A, B and C such that all 3 have same charge density. All three have same charge density. Now they want to know the potential. What is the total potential at a point at a distance r from their common center where r is less than a? So let us see. Suppose we have three shells of radius a, b and c. The q charge is distributed on all three. So let's say first one gets q1, second gets q2, third gets q3. Okay, and we want to know potential here at a distance r from center where r is less than a. So I think you remember, as we are inside all charges, potential at all these points will be same. Potential at all these points will be uniform. Okay, potential at all these points will be uniform and it will be same as potential of the center. So if we want to calculate potential of the center or this point, the potential will become, because of q1, at any point inside you will have k q1 by radius a. Because of q2 you will have k q2 by radius b, and because of q3 you will have k q3 by radius c. Okay, let's take k common. You will have q1 by a, q2 by a, and q2 by c, and q3 by c, q2 by b. Yes. Now, as they said, all three shells have same charge density. So shell 1 will have charge density as q1 by area, and area will be 4 pi a square. q2, the shell 2 will have charge density as q2 by 4 pi b square, and q3 will have charge density q3 by 4 pi c square. And since the total charge was capital Q, which is being divided into all three, so you can also say the charge density is equal to total charge divided by total area on which it is distributed, and the total area would be 4 pi a square plus b square plus c square. You can cancel 4 pi from everywhere. And now you know q1 by a. See, q1 by a, just make this equal to this, and q1 by a will be equal to bring 1a on this side. So q1 by a will be equal to qa by a square plus b square plus c square. Similarly, q2 by b will be b here, capital Q, b upon a square plus b square plus c square. Okay, so that's the logic we are going to use, and we are writing potential again. Take k common, and we have q1 by a as qa divided by a square plus b square plus c square, q2 by b as qb divided by a square plus b square plus c square, plus q3 by c as qc divided by a square plus b square plus c square. And if you take q common and LCM, you will see that the correct answer is Delhi. Okay, so that was a very simple question. In 2020, they simplified it a little and they gave only two shells. Otherwise, everything was same. So over to next question. This is again a very beautiful question, and I recommend you again to first solve it yourself and then see solution. Okay, I have made few corrections because the language was a little wrong. Okay, so just listen carefully. We have a solid sphere of radius r. Can you see that? We have a solid sphere of radius r. Carries a charge q plus a small q. So it has charge q plus a small q. The capital Q is distributed over its volume uniformly. The capital Q is distributed over its volume, and the small q charge is on a very tiny piece of it, part of it attached here. It has charge q and mass m. So they are saying a small q on a very small point like piece of it of mass m. This piece gets detached and falls in the gravity. This piece gets detached and falls in the gravity, okay, vertically. And after traveling a distance y, it acquires some speed. We have to know what is the speed. Actually, in the option we can say we have to find the v square. Okay. So let us solve this question. Obviously, when this piece is detached, it falls under gravity, and you know it will also experience electric force, but electric force and gravity both are conservative. So if you consider both conservative and define both forces potential energy, you can conserve mechanical energy and you can write, but remember, you have to write potential energy of both fields, electrostatic field also and gravitational field also. So I am writing conservation of energy, conservation of energy. I'm going to apply this at point A and B. Okay, so at A, electrostatic potential energy plus at A, gravitational potential energy plus kinetic energy at A will be same as at A, not at A, will be same as at B, electrostatic energy plus at B, gravitational potential energy or plus kinetic energy at B. When the charge was here, you can see it, you can assume it is still outside this sphere. Okay, you can still assume it outside this sphere, and if it is at the surface, you know its potential energy can be written as the charge q multiplied by potential because of capital Q at this point, and potential because of capital Q at this point would be k q by r. So this is the potential energy of small q initially. If you consider this as this point as gravitational potential energy 0 level, here the potential energy would be mgy because potential energy is mgh. Kinetic energy initially is 0 because it was just released from point A, equals to ub. Okay, when the charge reaches this point, its potential energy becomes q times potential at point B, and because of this charge, potential at B will be kq divided by distance from center, which is r plus y, okay, plus gravitational potential energy 0, and if gravitational potential energy is 0, kinetic energy will be half mv square. And now you can calculate kinetic energy. Okay, so let's bring this factor here. You will have mgy plus, take LCM, you will have k q and y divided by r plus y times r equals to 1 by 2 mv square. Divide this whole equation by m, so we will have mass here, and multiplied by 2. So let us see now what is the answer. Okay, so v square is going to be 2gy plus 2kqqy by r plus y multiplied by rm. So check your answers and you will have not this, because yes, v square as, yes, 2y we have taken common, so we have this as answer. Yes, you can verify, this will be your answer. Okay, so let's move to next question. Okay, we don't have next question, we have some more concepts related to conductors now. Okay, so conductors again is a very important phenomenon, and obviously they ask very simple questions based on conductors, so you must study it well. So now we will learn the behavior of conductors in electrostatic equilibrium. What do we mean by electrostatic equilibrium? The meaning of electrostatic equilibrium is actually there is no net flow of charge. And if inside conductor or on the surface of conductor there is no net flow of charge, means charge doesn't want to flow from one point to other. And if charge is not wanting to flow from one point to other, it simply means the 2 points are at same potential. That is why charge is not wishing to flow from one point to other. Okay, so if conductors are in electrostatic equilibrium, the one very important point that comes to our mind is the all points of conductor are equipotential. Okay, so all points on and inside conductors are at same potential when we talk of conductors in electrostatic equilibrium. The first point is all points are at same potential. If all points inside conductor or on the surface of conductor are at same potential, then conductor's volume will have no electric field. It will have no electric field. So net electric field inside conductor is zero. You all know if potential is constant, dV by dr is constant, and if dV by dr is constant, negative of dV by dr is electric field's component. So if potential is constant, electric field is automatically zero. So at all points inside conductor, the net field at all points inside conductor is zero. Okay. The third point is if you give some conductor some excess charge, it will jump to outside surface. So any excess charge if given to conductor resides on its outer surface. Always remember, resides on its outer surface. Okay. If conductor is spherical one, so it has a regular shape, then the charge density is uniform. But if it is irregular, what we observe is the charge density is more at sharper points. So where the conductor has sharper points, the charge density will be more. Okay. One more thing is that at the surface of conductor, just outside it, the electric field is given by the local charge density sigma divided by epsilon naught, and this field is directed towards outward normal. So n cap is an actually unit vector towards outward normal, but obviously if charge density is negative, it will be towards inward normal, or it will be inward. Okay. Few more points. As you know, electric field inside conductor is zero. So electric field lines inside conductors cannot exist. So electric field lines do not exist inside conductor, but as the conductor surface has charge, it can have charge. The electric field lines can start or terminate on conductor surface, but always normally. Why normally? Because conductor surface is equipotential, and you know at equipotential surface electric field can be normal only. Okay. So last point is when we have two conductors are connected by conducting wire. Okay. So if two conductors, maybe let's say we have two spheres, and if they are connected by a conducting wire, sometimes a charge flows between them, and the purpose of this flow of charge will be to make potential of the two same. So always remember, when two conductors are connected by a conducting wire, the potential of the two becomes same. Let us quickly review what we have studied till now. Suppose we have a solid conductor like this. Okay. The first point is at all points inside, potential is same. If potential is V here, it 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 is V here. Even on the surface also, potential is same. The second point is at all points inside, electric field is zero. Okay, electric field is zero. If you give this conductor some charge, it will distribute on outer surface only. Okay, it will distribute on outer surface only. So outer surface will have only charge. But as you can see, this part is sharper than this part. So if here we have charge density sigma 1 and here we have charge density sigma 2 will be more than sigma 1 because charge density is more at sharper points. Okay. The next point we studied was electric field on the surface of conductor. So if you want to know the electric field just outside the surface of conductor, just outside it, it will be outward, and electric field is given by, if charge density here is sigma 1, we have electric field as sigma 1 by epsilon naught. Okay, and if charge density is sigma 2 here, electric field here will be sigma 2 by epsilon naught. So electric field just outside the surface of conductor depends upon local charge density, right? The next point was, yes, the electric field lines do not exist inside conductor. So we will not see any electric field line inside conductor. If it is a positive charge conductor, the electric field lines will start from its surface, and electric field lines only cut conductor surface normally. So always remember this point. Conducting electric field lines will cut or can cut conductor surface only normally. Okay. If this charge is negative, they will terminate on the surface, but from outside only. And when two conductors are connected by conducting wire, so if we have two conductors of say charge Q1 and Q2, of say charge Q1 and Q2, and you connect the two conductors, the charge may flow from one conductor to other or other to one depending upon their potential. Okay, their potential, and finally they will be having same potential. Finally V1 will be same as V2. Okay, so remember these results, and let's move to next slide. As you know, if we place two charges close to each other at a separation of r, this configuration has some energy. If you place 3 charges or n charges, this configuration too has some energy. So if we have a hollow shell on which charge Q is uniformly distributed on its surface, you can still imagine large number of particles are arranged in uniform manner over the surface. And if large number of particles are arranged on its surface, this configuration too has some energy. And if this too has some energy, this energy is called self-energy of this configuration. Similarly, if charge is distributed over the entire volume, this too has some energy, and this is called the self-energy of this system. Anyone can derive self-energy, okay, and the self-energy of the system can be derived from this formula, half epsilon naught E square dV, because you know this is the electric energy density, and by multiplying in electric energy density with elemental volume, you know the energy in this volume, and for finding energy of bigger volume, you can integrate this law. Okay. But I want you to remember few results. Okay. So if we have a hollow shell and charge is on the surface only, you have to remember that electric field inside is 0. And if electric field inside is 0, there is no energy inside. Okay, this table belongs to self energy of the system. So if we have a hollow shell and distance of point or distance of points is from center actually is less than the radius of the shell, means we are inside the shell, we do not have any energy. Okay, we do not have any energy. All the energy is stored in outside region. And in outside region, energy is kq square by 2r. Remember this point, kq square by 2r. Okay. So if inside the shell we have no energy, if outside the shell we have kq by 2r energy, the total energy associated with this shell is the sum of these two, and it is kqr by kq square by 2r. This is the self energy of the hollow shell, right? But if we have charge distributed over entire volume of the sphere, we also have electric field inside, we also have electric field outside. So we have energy inside also, we have energy outside also. Just remember the formula. Energy outside will be same as it was in hollow shell, kq square by 2r, kq square by 2r. But energy inside comes numerically equal to 1/5 of energy stored outside. So remember this point, energy inside is 1/5 of energy outside, and if you add these two, you get energy of total self energy of this system. So remember this point. In hollow shell, we do not have energy inside, we energy have only outside. And when it comes to solid charge, the energy is inside also, outside also. And results are in front of you. Let us solve few problems based on these facts. First, consider two charged metallic spheres S1 and S2 of radii R1 and R2. Okay, so we have two spheres S1 and S2, radii R1 and R2, right? The electric field E1 on S1, E2 on S2 on their surface are such that E1 by E2 equals to R1 by R2. Okay, so let's write this result. E1. Let's not write this result directly. Let's write one step ahead. Actually, you all know if charge on first is Q1, charge on second is Q2, the E1 is K Q1 by R1 square divided by E2 is K Q2 by R2 square, and this result they have given as R1 by R2. So from here you can write Q1 by Q2. Okay, you can write Q1 by Q2 as Q1 by Q2 as R1 cube by R2 cube. Please check it. R1 cube by R2 cube. Okay, and if you write Q1 by Q2 as R1 cube by R2 cube, they are asking us what is the ratio of potential on the two surfaces. Okay, so let us find ratio of potential. So V1 upon V2, you all know V1 is K Q1 by R1 and V2 is K Q2 by R2. Cancel the K and put Q1 by Q2 as R1 by R2 cube. So you will have Q1 by Q2 as R1 by R2 cube, and we have one more R2 and R1 like this. This is cube actually. Okay, so one power gets cancelled and we are left with R1 square by R2 square as V1 by V2. So correct answer is D. Okay, let's move to next question. Yes, this is a very good question again in 2020, and they say there is a uniform spherically symmetric surface charge density at a distance r naught from origin. So all the charges at a distance r naught from the origin. The charge distribution is initially at rest. Okay, so just imagine if all the charge is at a distance of r naught from origin, you can imagine all the charge is distributed on a shell, on a spherical region, hollow spherical region of radius r naught. Okay, let's see what's the total charge. They haven't said anything about the total charge, but let's assume the total charge is Q and it is on the surface of a sphere of radius r naught, as you can assume, because they have said all the charges at a distance of r naught from center. Now because of mutual repulsion, this charge will fly away. And when the charge flies away, obviously their speed grows. So when the radius becomes capital R, the charged particles are on a bigger sphere of radius R, moving away like this. Like this. And now the sphere grows. What they are asking is, we have to guess the figure, the graph that represents best the speed of the distribution as a function of its instantaneous radius. You know, as they are moving under electrostatic field, and electrostatic field is conservative, you can again conserve energy. So I can write initial potential energy plus kinetic energy equals to final kinetic energy plus final potential energy plus final kinetic energy. As you know, initially the charge is on a hollow sphere, then its self energy can be written as kq square by 2r0 because radius is r0. And initially all the particles were at rest, so kinetic energy is 0. But when they reach at radius capital R, the energy becomes kq square by 2r, right? Because of symmetry, actually, we can say all will be at same separation from center and all will be having same speed. So if total mass of configuration is m, the kinetic energy can be written as half m v square, because we can assume because of symmetry every particle must be traveling with same speed. Okay, so now you can easily see the v square or half mv square. I think 1 by 2 got cancelled from everywhere, so v square equals to kq square by m and 1 by r naught minus 1 by r. So we can clearly see the speed. As r will increase, speed will decrease. As r will increase, speed will decrease. Sorry. I said it wrong. When r will increase, this factor will decrease. And if this factor will decrease, this factor will increase. So speed is increasing. Okay, speed definitely increases, right? But it will not increase always, or it will not increase for infinite time. When the radius of configuration becomes very larger than r naught, I can say then 1 by r is nearly negligible as compared to 1 by r naught, and then we can say v final square equals to kq square by m r naught when the radius will be very large, like infinity. Okay, and then I can say the speed will approach to this result. Okay, so the particles will finally move almost with this speed. So I must say speed increases and will approach a constant value, this, and the best graph I see is this. Speed is increasing and is approaching some final steady state value. So correct answer is D. Okay, students, let's move to our next question. Okay, keep studying. I know the lectures are long, but I already said see these lectures in maybe steps of 3 or 4, so they will be a very good learning tool for you. Okay, now in this question they say two isolated conducting spheres S1 and S2 of radius 2 by 3r and 1 by 3r. So we have two spheres, one has radius 2r by 3, one has radius r by 3. Okay, and they have charges 12 microcoulomb and 3 microcoulomb. 12 microcoulomb and minus 3 microcoulomb, right? And are at large distance from each other. You can say this distance is almost infinity. They are now connected by a conducting wire. And if they are connected by a conducting wire, a long time after this is done, what are the charges on, what are the final charges on them? This we have to know. Okay. I told you few minutes before that when you connect those two conductors by a conducting wire, the potential of two becomes equal and charge flows if required. So please assume final charges as Q1 and Q2. Okay, beta. Assume final charges as Q1 and Q2, and now the potential of first will be K Q1 divided by 2R by 3, and potential of second will be K Q2 divided by R by 3. So from here, if you cancel K and R, you will have 2Q2 as Q1. 2Q2 as Q1. Okay, 2Q2 as Q1. So finally, you can say Q1 will be twice of Q2. The charge on 1 will be twice of charge 2. Now you see the total charge on them is 9 microcoulomb. The total charge on them will remain conserved. So total charge will remain conserved, and total charge on them will be 12 minus 3, that is 9 microcoulomb. And Q1 is twice of Q2. Q1 is twice of Q2. So obvious answer is A, because you can see the sum of these two charges 9 and Q1 is twice of Q2. Okay, so that was a simple question, I think. Let's move to next question. Here in this question, they say two charged spherical conductors of radius R1 and R2 again. You can see they have asked multiple times questions of same type. Okay, so two charged spherical conductors of radii R1 and R2 connected by a wire, and then ratio of surface charge density of the sphere is. When they are connected by a wire, obviously their potential, the final potential will be same. The same thing we discussed in previous question. And if their final potential is same, I can say final charge, say Q1 by R1. Let's say the first sphere has charge Q1 as final charge. The second has Q2 as final charge. The potential will be same. And Q1 can be written as charge density multiplied by area, which is 4 pi R1 square by R1. This is Q1. Please verify. Equals to K times charge density 2 4 pi R2 square by R2. One R2 got cancelled, one R1 got cancelled, and we have, by eliminating everything, sigma 1 R1 equals to sigma 2 R2. And if sigma 1 R1 equals to sigma 2 R2, obviously sigma 1 by sigma 2 is R2 by R1. So correct answer is obviously B. Let's move. Okay. So that's all for today, students. I hope you enjoyed this lecture very much, and I again hope you have learned a lot. Okay. All the best for your exams. Thank you. Thank you so much.